Okay, hello everybody. Welcome to the conference topics in geometric analysis. So I will say a few words before we start as a director of the Georgi Center, and promise I won't take much time. So the center was founded about 25 years ago, formerly as a research laboratory of Scuola Normale, but with a mission of creating gathering opportunities for the whole mathematical community in Pisa. So in addition to Scuola Normale, there's of course the University of Pisa, and there's a small group also at Scuola Superiore Sant'Anna. And these institutions, especially the former, contribute also substantially and financially to the activities of the center, and also with the help of the Sansone Foundation. So the main activities since the start have been workshops, schools, and intensive research periods. And we have visiting positions of two kinds to perform research in pairs, short-term visiting positions, and we have 2 years postdoctoral positions. The center also runs a colloquium series, and essentially that's all I wanted to say. So I would like to thank especially the other organizers of the workshop, Alessandra, and also the staff of the center for the constant and valuable support. So then I changed my badge from a director to organizer. Okay, so people usually change virtual hats, but I have a physical badge. And so as an organizer, I would like to thank, of course, all the speakers and the participants for coming. And I would like to acknowledge some funding from European Union, the Next Generation EU funding, from Alessandra, Dipartimento di Eccellenza from the University of Pisa, another grant from Alessandra, News Project, funded by the University of Pisa, the project PRIN 2022, and of course, Centro de Giorgi. And I guess we can start with a program and the first talk by Garrett.
Right. Thank you very much for the invitation. It's wonderful to be back in Pisa at this conference. And today I want to talk about concepts of quasi-local mass. So let me set the stage. So we are going to talk about Riemannian three manifolds. And I want to assume they are asymptotically flat with one of the usual definitions, such that you have a mass at infinity, usual decay conditions, and I assume that the scalar curvature of the metric is non-negative. And if there is a horizon, so if the boundary of M3 is not empty, then I assume that the mean curvature of the boundary is equal to 0. I assume this is the outermost minimal surface, and the interpretation is that this is the outermost horizon of an isolated gravitating system in general relativity. And the prime example would be spatial Schwarzschild, which would be R3 outside the origin with the metric GM, standard metric with a conformal factor 1 plus m over 2r to the 4. And this is the m is the mass of this static black hole. And let me call this M3 little m. And the picture you have in mind is asymptotically flat near infinity, and then you have a single black hole, and this is the horizon, and numbers are such that 16 pi m squared is the area of this horizon. That's an important example to keep in mind. And then the other terms I need is, if I have a two surface, then I denote the area radius of the two surface such that this formula is true. And the other thing I need is the Hawking mass of a 2 surface. So if sigma 2 is inside the 3 manifold, I denote the Hawking mass of sigma 2. This is 1/2 the area radius of sigma times 1 minus 1 over 16 pi, the integral of the mean curvature squared over sigma. And you notice that in Euclidean space, most of the time it's negative because integral h squared is bigger than 16 pi, and it's equal to 0 in Euclidean space if and only if it's around sphere. That's an important quantity used by Hawking to measure suggested by Hawking to measure the mass inside a boundary of this 3 manifold. The technical tool I need is inverse mean curvature flow. So this is a flow of position 1 over h times the normal in case h is positive. And this has some key properties. Almost the definition is that the area increases exponentially at each point. And then the relevance to what we're doing today is the Garrosh monotonicity formula, namely if sigma t is a solution of mean curvature flow, then the change of the Hawking mass of sigma t is non-negative, and we actually need the precise formula. This is the area radius divided by 32 pi times the integral of sigma twice gradient log h squared plus the trace-free part of the second fundamental form squared plus the scalar curvature of the 3 manifold and plus 8 pi minus 2 times, so this is a d mu plus 8 pi minus 2 times the integral of the Gauss curvature over sigma. And then you see that this is greater or equal to 0 if sigma is connected. And I think this is a monotonicity formula, and it leads to a theorem, leads to the Penrose inequality, but today I need it in a more strong form. So this is the old theorem by Tom Illman and myself. And it says that if you have any outward minimizing surface, embedded surface in such a 3 manifold, so suppose sigma 2 contained in M3G is outward minimizing, meaning you cannot wrap it in any cheaper way with less area. Think of it as a boundary of a domain, outward minimizing. Then it is true, and if it is connected, and connected, important, then the Hawking mass of sigma is less than the ADM mass of the 3 manifold. And this in particular implies as a special case, if the area of the mean curvature of sigma is equal to 0 and we have a horizon, then this implies that the area of sigma is less than 16 pi ADM squared. Okay, but I really want to emphasize that it's not just true for the horizon, for any outward for any outward minimizing surface, you get this inequality. Now, what I want to talk about now is concepts of quasi-local mass. And Robert Bartnik gave some criteria what properties it should have. So suppose omega g is a Riemannian manifold again, but not complete. Think of a domain. And again, scalar curvature greater or equal to 0. Then you want a quantity, quasi-local mass of omega g in R that has certain properties. You want, first of all, monotonicity. So if omega 1 is isometrically contained in omega 2, whenever I write it like this, I mean an isometry from omega 1 in omega 2, then you want the mass of omega 1 to be less than the mass of omega 2. Secondly, you want the mass of any omega to be greater or equal to 0. And thirdly, you would like that it is related to the ADM mass, that if you have a sequence of omega I exhausting the whole 3 manifold, then you want that the local mass converges to the ADM mass. And finally, you would like to have rigidity. You would like to have the reverse conclusion if the mass is equal to 0, that first of all, this is locally flat. Let's call this A. And B, maybe you can even prove that omega g, which is of course stronger, is isometrically immersed in flat space. Okay? And Robert Bartik made a suggestion what such a mass could be, and he defined what I call the Bartnik capacity of omega g. He said, let's take the infimum over all masses, ADM masses of extensions M3G. So this is omega g is again isometrically sitting in M3G. But you have to make sure that omega is not going to get hidden behind a tiny black hole, because then you can easily make this 0. So you assume that there is no minimal surfaces in M3G. That was his original definition. And M3G has non-negative scalar curvature and, of course, asymptotically flat. And now, with this definition, the first two properties are going to be okay. The one is okay by simply, if you have a larger domain, you have less competitors, so the mass gets bigger. And the second one is true by the positive mass theorem, right? Because all of these surfaces, or these 3 manifolds of non-negative scalar curvature, have positive mass by the positive mass theorem. So you get the non-negativity. And it turns out you can prove 3 and 4a with inverse mean curvature flow. So 3 and 4a follow from inverse mean curvature flow. And let me just show you 4a. sketch of the proof, suppose omega g is not flat, pick P naught in omega, where it is not flat. So here you have this domain, and you pick a point where it's not flat. And then you solve inverse mean curvature flows starting from tiny spheres. In fact, starting from this point, you solve IMCF solution. And you can show this is going to be a smooth solution. There's this concept of weak solutions where the surfaces can jump. And I should have said that these monotonicity formulae still are valid for the weak solutions. But the weak solutions can jump. And then we can have to interpret this formula up there more carefully. But here, there is a small radius around P0 where they don't jump. You can, because there's no way to sort of optimize area as long as the surfaces are small by jumping somewhere else. So you have this little annulus where you have a smooth solution. I call this an IMCF core at P naught, because I need it later. And then along this solution, you get the monotonicity formula up there. So the Garrosh formula tells you that if the that you pick up some mass because you are on sphere, so the last two terms cancel out. So you pick up some mass if the scalar curvature is positive, for example, or if A0 squared is non-zero, or if the mean curvature is not constant. So if the mass is, and this is independent of the extension, pick up Hawking mass of sigma t, unless you have r equals 0, you have A0 squared equals 0, and you have h equals constant. And you pick up a certain amount of mass independent of what extension you choose, because it only depends on this little region around the point P naught in omega itself. So, but if you, in this annulus, have these three conditions valid, a little bit of work shows that this must be then some spatial Schwarzschild. You are led to an ODE, it's rotationally symmetric, but then you realize that Schwarzschild has to be the one with m equals 0, and that proves this rigidity result. B was left open for a long time, and only in 2024 Si Dong and Antoine Song proved that this, using Gromov-Hausdorff convergence of a minimizing sequence, suppose you have a sequence of extensions where the mass is going to 0, that it has Gromov-Hausdorff convergence of mass minimizing sequences to flat space. And that settles. And that settles P. So all the so this is beautiful in that sense. However, I claim I'm not completely happy with it anyway, because this Bartnik capacity, just because of this rigidity, has a property which in some physical situations is maybe not so desirable. So one deficiency is suppose we take one of these Schwarzschild regions here. Suppose omega g is sitting inside one of these spatial Schwarzschild regions, but not homologous to the boundary. Let me just write outside the boundary. Then from a physics point of view, it should not contain any energy. It should not contain any mass, right? But this theorem says, because it's not flat, it has to have mass. So we get that the Bartnik capacity of omega g is positive against physics intuition, at least against some physics intuition, right? That all the energy should be in the horizon, and there shouldn't be any energy outside of the horizon. So this seems to contradict that. So can we massage the definition of quasi-local mass to improve on this problem? Now, clearly this has to do with the rigidity and this inequality, and the inequality followed from the positive mass theorem. So now if you want to have a result that is sort of also sharp on Schwarzschild, it has to somehow use the Penrose inequality. So let's let me give a definition which I hope can help in this direction. So I erase this. So first of all, I define what I mean by an exterior region. An exterior region, M3G, is as before. It's asymptotically flat, scalar curvature greater or equal to 0, no minimal surfaces. And if the boundary of M3 is not empty, then I assume it to be outward minimizing. Which is stronger than just positive mean curvature. So I'm not restricting myself to horizons. I just assume I have a boundary which may be some positive mean curvature surface, but I also want this global property that it is outward minimizing. And then in particular, this implies, by the theorem I stated on this blackboard, this implies that on these exterior regions, the ADM mass, M3G, is bigger than the Hawking mass of the boundary if the boundary is connected. If it's not connected, then it's still true for the largest boundary component. And then let S be the set of all these exterior regions. And then I make two definitions. So first of all, I define capacity 1 of a domain omega g, similar to Bartnik as the infimum over all isometric extensions, but now I take the ADM mass of the extension minus the Hawking mass of the boundary, and I do this over all M3G in S. So as before, I don't allow minimal surfaces outside, but now I allow an inner boundary that is outward minimizing, and I subtract its Hawking mass. This includes also the case where this inner boundary shrinks to a point, and then you have the original extensions without an inner boundary as before in the Bartnik definition. So this is a larger class of competitors than in the Bartnik definition. So this is clearly slightly smaller than what Bartnik defined. Or now, sometimes in physics, this leaves open which Schwarzschild omega might be in if it's zero, right? This quantity here has the property capacity 1 omega g is equal to 0 for all omega g sitting in any M3M. All right? I don't say which one, but now sometimes you know how big your inner body is. We know what the mass of the sun is, and we want to measure a small planet, a meteor, whatever, outside the sun, and then we know what this number is. So you could also be tempted to define the capacity 2 of omega g to be the infimum of the, and then you know the number. So let's put the number m0. So given a domain, a metric, and a number m0, so given omega g and m0 positive, define this to be the infimum of the difference between the ADM mass of m3g minus this number. And take this for all m3g in S such that the Hawking mass of the inner boundary is exactly equal to this number m0. Okay. And this now has the property that this capacity is equal to 0 on any domain in this particular Schwarzschild. So capacity 2 of omega g is equal to 0 for all omega g just in this Schwarzschild m0. And let's see what are the properties. Clearly, you have the monotonicity again. So one monotonicity, trivially true. The positivity follows from the theorem. Capacity I of omega GB is greater or equal to 0 for both I equals 1 and 2 by the theorem that I just had on the board. And again, the monotonicity near infinity can again be proved by inverse mean curvature flow, that you approach the ADM mass for large regions. And the hard part is, of course, the rigidity part. So what about rigidity? And I'm thankful to Carla for the discussion we had 2 weeks ago in Stockholm. I wasn't, and she made my thinking clearer, namely that it's wrong because of the following picture. You take Schwarzschild and you just add on a long cylinder. And then you take a domain, omega. In this picture, you can do this, smooth this out with an arbitrary small error. And then you take a domain which sort of straddles I'm not very good at drawing this, but you know, it's the domain is sort of reaching from the proper Schwarzschild region down into this cylinder. And then you can clearly approximate this guy, this three-manifold. This wouldn't quite fit our definition, because this boundary is not outward minimizing. Only that boundary is outward minimizing, right? So this would not be a valid competitor, but I can create valid competitors by just moving this in a tiny little bit. And then I can approximate by, can find extensions M3I, GI, actually it's the same manifold, such that the ADM mass of M3I, GI minus the area of the boundary, the Hawking mass of the boundary, actually tends to 0, and the domain is not properly sitting inside some Schwarzschild. So the conjecture has to be somehow slightly more sophisticated than just saying omega itself is part of Schwarzschild, right? You only can argue that this part above the outermost horizon is going to be in Schwarzschild, not that part down here. Now, how can you distinguish between the two parts of omega? Now, in this part, in the lower part of omega, you have positive scalar curvature, right? Because you have the cylinder and you have positive scalar curvature, whereas up here you have 0 scalar curvature. And when you look at the monotonicity formula, which unfortunately I erased, you saw the scalar curvature turned up in the monotonicity formula of the Garrosh monotonicities. So if we now choose on these MIGI, they all have boundary, right? If we start the inverse mean curvature flow on all of them, so consider the weak solutions of IMCF on the MIGI, starting at the boundary, and this gives you surfaces sigma t that are sub-level sets of some function UIT. Then from the theory of these weak solutions, you get that the gradient of the UI and the sup S actually, plus the sup of the UI, are uniformly bounded, independent of I, just depending on omega. So on omega, you get uniform bounds on the gradient and the height, y. And then there, in the work with Tom Illman, and there's a compactness theorem. So the UIs converge to a weak solution of IMCF on omega. And now formally, the when you look at ddt of the Hawking mass of this sigma t, what you can justify for the weak solution is that you get this on the right-hand side, in particular the positive term coming from the scalar curvature. And if you write it with the co-area formula as a volume integral, you get volume integral over omega of the scalar of r times du times d vol. Right? It was an integral of r over the surface, so now if we turn this into a volume integral with co-area, you get this. So now this tells you pick something up in the region where r is positive and du is positive. The only way you can have rigidity is that you are not picking up any r is if du is 0. But du is 0 is a jump region. So we don't pick anything up as long as r is 0 in the jump region. R is positive only on the jump region. So this would be positive if both r bigger than 0 and du positive. So this, with this, you get that the positive part of the scalar curvature must be inside the jump region of the final inverse mean curvature flow. So the support of R it must be contained in the jump region of IMCF on omega. And this fits exactly to this picture, right? This, if it jumps, it goes up to the horizon, and then we expect it to be Schwarzschild. So now it is known that if you're in the region where the scalar so can show, on the other hand, that the region, that part of omega where r of x is equal to 0 has to be static. With the same arguments that Bartnik in his static metric conjecture argued that the minimizer of the mass must lead to a static metric. So this is how far I got. I have this region where scalar curvature is big, has to be in the jump region, and the other part where r is 0 has to be in the static region. So now I think it's fair to formulate a question, or I'm not daring to really call it a conjecture, but it's a bit bold. My question would be, suppose this capacity 1 of omega g is equal to 0, can you conclude that that part of omega where r of g is equal to 0 is contained in some Schwarzschild? That would be, I think, the appropriate rigidity statement ruling out the example here. Of course, these examples are related to the work of Shane Mantoulidis, where they showed that the Bartnik minimization conjecture cannot be quite true if the boundary is a horizon. Right? So see also Mantoulidis, Shane, and I've been informed also recent work by Kala. Right, so that's one comment I wanted to make on the concept of quasi-local mass of Bartnik. The second part, I want to talk about something that is related to a question that Kip Thorne once posed in terms of the size of regions where you have a lot of mass. He said, you know, the radius of a region where you have a lot of mass cannot be too big. And let me read it to you, what I found in the internet. He said the total mass of an object that is concentrated such that it resides in a perfect sphere with radius equal to the object's Schwarzschild radius, he means 2m. So if you have something that is in a region radius r equal to 2m, the total mass, then there has to be a collapse to a black hole. He even said, if not true, then no black hole forms. So to make this precise, you have to have a notion both of quasi-local radius and quasi-local mass. So I think the task Kipthorne gave us is find notions of quasi-local radius, let's call it RQL, and of some domain, omega g, and quasi-local mass, and MQL, omega g, like we just discussed, such that in particular, you get that the radius of a domain somehow has to satisfy 2 times has to satisfy this inequality. And also you could ask how much matter can there be in terms measured in terms of the scalar curvature. So that would be sort of the second question on suppose the scalar curvature of G is greater or equal to some lambda bigger than 0 on omega. How large can the radius of omega G be? And Shane Yao gave one first answer in a beautiful paper in 1984. It's a short paper, but very, very beautiful. And they made a definition. So they said, define the radius, let me call it radius Shane Yao, of omega G to be the sup over all closed curves. And then you take the sup of all radii such that the tubular neighborhood around gamma of radius r, if r is very small, then you cannot span, then any minimal surface spanned by gamma cannot completely lie in this tubular neighborhood. But if I make it very large, then I can span a minimal surface. So I take the largest r such an Rg does not contain a minimal surface spanned by gamma. And then you optimize over R, over all these curves gamma. And note that you get, with this definition, you get that the Shane Yao radius of a ball sitting in Euclidean space is just exactly 1/2 R. So there's a discrepancy. And then they use stability of minimal surface theory and very beautiful variational calculus to prove the following. They show that if the scalar curvature is bigger than lambda, then this Shane Yao radius has to be less than 2 pi over square root of 3, I think, times square root of lambda. So they get a rather sharp bound on the radius. Yes, I got the number right. And we had a student in Tübingen who actually did this for certain neutron stars with a certain state equation, and this number leads to something like 20 kilometers, and the observed neutron stars are something like 12 kilometers. So it seems to be a pretty good estimate. Now, I claim that with inverse mean curvature flow or some other ideas, there may be other definitions of quasi-local radius that are interesting to study. So let me do quasi-local radius by inverse mean curvature flow. You could say, given the domain omega and any point P, look at these inverse mean curvature flow cores. So you start inverse mean curvature flow from tiny spheres. And then I look at the largest smooth solution that I can do this way. And I define the IMCF radius of omega g to be the sup of the area radius of sigma t, where sigma t is an IMCF core at any point P in omega. With this definition, you see immediately the IMCF radius of a ball in Euclidean space is exactly equal to R, because it's not, yes, and you see that the IMCF of omega sitting in R3 is just the inner radius of omega, simply the largest smooth sphere that you can, the radius of the largest ball you can embed inside omega. So in that sense, you don't give up a factor 1/2, like in the Chen-Yao definition, and you can then use the monotonicity formula the same formula that I used to prove the rigidity, right? This one, ddt of the Hawking mass. You can then see that if the scalar curvature is bigger than lambda, you can integrate this up and combine, on the other hand, use the fact that the Hawking mass of any surface, remember this was this formula, this is always less than 1/2. And on the other hand, you get a lower bound from the monotonicity formula from this, if you have a lower bound on the scalar curvature. So assuming the same lower bound that Chen-Yao got, then you can use the monotonicity formula and this upper bound on the Hawking mass to see that this IMCF radius of omega g satisfying such a lower bound on the scalar curvature must be less than square root of 6 divided by square root of lambda. And you can also show that you have equality exactly if in the limit integral h squared is 0, so you have a minimal surface. And with a little bit more work, similar as in the rigidity case above, you see that the only way you get equality is this picture where you have Schwarzschild attached to a hemisphere of constant scalar curvature. That's the equality case for this inequality. So it's sharp in that sense. Final thing I wanted to tell you is a third way to define. By the way, in this case, because of this inequality here, if you define, if you define the IMCF mass to be the sup of the Hawking masses over these sigma t in an IMCF core, then of course you get the trivial inequality. This is just by the setup that R IMCF is less than 2 MIMCF. So in some sense, if you just after this inequality, it's cheating. But I think concerning the lower bound on the scalar curvature, it's sharp and maybe interesting. So I think there's one other way that could be looked at, and that's a spectral definition of quasi-local mass. And for this, I remind you, if you have a surface, if sigma is a surface sitting in M3G, actually for any dimensions, then the stability operator, the Jacobi operator, let's call it Jacobi operator because I don't apply to stability yet. L sigma is given by L sigma of u equals minus Laplace u minus u times the second fundamental form squared plus the Ricci curvature of the 3-manifold in normal direction. And let lambda be the first eigenvalue of this operator, restricted to functions that have 0 integral. So let lambda 1 be the infimum of the Rayleigh quotient the mu where integral u d mu over sigma x equal to 0. And now I let my spectral radius of a domain be the let me just that I get the constant right. Yeah, I take the supremum of the area radius of all sigma that such that sigma sit inside omega g with lambda 1 greater or equal to 0. And I use a second derivative for the mass, so the spectral mass of a domain omega g is going to be the sup of 1/6 lambda 1 Ra to the cubed of sigma, where sigma is contained in omega g with lambda 1 greater or equal to 0. Why this formula here? 1/6 lambda 1, the scaling is right? Lambda scales like 1 on distance squared, so this scales like distance, like mass should. And let me just tell you the properties. Of course, the formula is suggested by Schwarzschild. So notice that, of course, so here's the properties that M spectral of a domain omega g sitting in R3 is of course 0, because the best you can do is lambda 1 is greater or equal to 0 only on the round spheres, and in fact you have zero eigenfunctions which are the translations in R3. Yeah, so in R3 you get exactly 0, and lambda 1 equals 0 corresponds to the 3 translations. Now if you do it in Schwarzschild, so if you have a boundary of a ball of radius r inside one of these, M3, m in one of the Schwarzschild metrics, then of course R has to be bigger than m over 2, which is the horizon. Then if this is sigma, then you get that the spectral mass of this sigma, the lambda 1 of sigma, is exactly, yeah, maybe I should write it like this. Lambda 1 of sigma, these are constant mean curvature surfaces, right? These, in this picture here, all these spheres here are constant mean curvature surfaces, and they are stable, and the first eigenvalue on each one of them is 6m over Ra cubed. On each one of them, right? It's not depending on R. And now you can just solve this formula to see that you have equality, and this explains this formula. I just turn it around. Instead of computing the first eigenvalue of these surfaces, I turn it around, make it into a definition of mass. Yeah. And so this explains the particular formula, and now, of course, it's only valuable if I can prove something else. So let's see. The properties I can prove, and I'm running out of time. That's why I'm just give it to you without proof. I can show that if, again, the scalar curvature is bigger than lambda than 0, then I can prove that the spectral radius of a domain omega g is less than exactly the same constant. Again, this sharp constant, same inequality like for the inverse mean curvature flow radius. And I can show that the inequality asked for by Kip-Thorne is true. So you get that the R is less than 2m spectral over omega g. And finally, I can show that the Hawking mass is larger. So you get that the spectral mass of a domain omega g is, or let's do it for one surface. This implies it also for m. This is less than the Hawking mass of sigma. And a key point in doing this is I have to use this so-called Hirsch trick, where you use clever eigenfunctions on a sphere that you take a conformal diffeomorphism to S2, so you can essentially take the coordinate after conformal change, the coordinate functions in R3 of an S2, and then you can precisely compute the Dirichlet integral and the definition of the spectrum, and you get sharp estimates that allow you to prove these things. Thank you.
Are there any questions?
Yeah, thank you for the nice talk. I have a question about this IMCF radius, actually.
Yep.
I don't quite understand it yet because it's picking the optimal point, right? So it is, so the supreme.
Well, I optimize over all points. If you pick a
Right.
bad point, then you get.
Right. I just wonder how you can get any kind of rigidity result, because you can change the manifold somewhere else in any way you want in regions where the point is not chosen optimal.
Oh, the rigidity,
So
I didn't claim any rigidity here.
so there's an equality case, which is, wait, that equality.
Oh, for this inside this particular core where
So where you cap off the black, the horizon there with this ball of radius.
I claim then there must be some, there must be some region. I take this inverse mean curvature flow, and if I get equality in this formula, I get that all these terms, that h has to be constant, a0 is 0, and meaning the two principal curvatures are the same, and the scalar curvature is 0. And then I pick this, and then I get this region where I have an ODE.
Yeah.
And I solve this ODE, and then I find that, yeah,
So
and
the
I
claim-
compare it to the evolutionary equation of the mean curvature, right? And this way, there's an intermediate step where you show that the Ricci curvature in that region must have just two eigenvalues. In other words, one in the radial direction and two eigenvalues in the tangential directions to the surface. And once you have that knowledge, that these two tangential eigenvalues are the same, you compare it to the evolutionary equation of mean curvature, and you see that, in fact, all three constants are the same, and you are on the sphere.
Okay, so you're basically claiming that there must be a region like this with
Yes,
the cap region,
right.
but not the whole manifold has to look like this.
Yeah, no,
Okay,
yeah.
I see.
I have one region which
Yeah,
looks
right.
like this capped region.
Okay,
Yeah,
thank you. Thank
yeah.
you.
Yeah.
So, do you have any idea how to compare the inverse mean curvature flow and spectral radius and mass?
Well, I get this one here that I can compare
Right.
it to the Hawking mass. And that, I mean, that gives you also that if you take the soup over these, that you have the right inequality, but I don't see how I can get any quantitative between them. I think the spectral mass is somehow, you know, it's just striking that you can prove these things. Whether it's really useful, I don't know, but it's harder to prove the rigidity result if the spectral, I didn't claim it here, if the spectral mass is equal to 0, to prove that the domain is flat or something like that. That would be harder. But I think it may be useful in some situations because, for example, the center of mass near infinity, for the most weak decay conditions near infinity, people use L2 methods, right? And they work with the spectrum. So I think it is good to know this relation between the mass of spectrum, that it goes both ways. Yeah.
Thanks.
All right, so if there are no further questions, we can thank Gerard again. Right, so our last speaker this morning is Marco Pozzetta from Politecnico di Milano, and he will talk about the sharp spectral splitting theorem.
Thank you. Thank you very much for the introduction and the presentation, the invitation to speak at this very nice conference. Thank you very much. Okay, so yeah, I'm going to talk about splitting theorems in Riemannian geometry, and more precisely, I will present a result obtained last year in collaboration with Gioacchino Antonelli, who is at New York University now, and Kai Shu, who just got his PhD from Duke University. So let me first start with the setting I will consider. So the setting more or less will always be the following. I will consider MG a smooth n-dimensional, so little n is always going to denote the dimension, n-dimensional, connected, smooth, I said smooth, complete Riemannian manifold without boundary, and most of the times, I will assume that M is non-compact. So we will study non-compact manifold. So M is non-compact. So most of the times, M will be as it is here. Okay. So we're going to discuss spectral splitting theorems. And so let me recall first the very classical splitting theorem in Riemannian geometry by Chigger and Gromol. The theorem is the following. It's a classical theorem by Chigger and Gromol from 71. It is the following. Suppose that you have Mg, as before, such that the Ricci curvature is non-negative, and such that there exists a line, such that there exists gamma from R to M which is a line. Then something happens. What is it, a line? A line is an infinite minimizing geodesic, okay? So let me just draw a picture here. Maybe the blackboard is the ambient manifold. This is my infinite geodesic. And so the length from one point to another length is equal to the distance between those 2 points. Okay, so it's an infinite minimizing geodesic. So then something happens. The manifold splits. So M splits as a product n times r. So I will always use this terminology that a manifold splits as a product. It means the following. It means that it splits isometrically. So whenever I will say splits, I mean that M with its metric G, Mg, is isometric to a Riemannian product, n times r, with the product metric, so Gn plus dt squared in this notation. And it is isometric, and n is compact. N is actually compact in particular, but not too important now. Okay, so this is very classical, celebrated theorem by Chigger-Gromol. And it has a useful corollary. So the useful corollary is the following. Take Mg such that Ricci curvature is non-negative, and such that M has at least 2 ends. It has at least 2 ends. Well, yeah. Oh yeah, right. Yeah, sorry. It's in the other case, of course. Yeah, sorry. Of course. Thank you. Yeah, no, I'm sorry. In this case, it is compact, of course. Thank you. So it splits isometrically. We have the following corollary. Very useful corollary. It is if you have non-negative Ricci and you have 2 ends now. What does it mean, 2 ends? It means the following, that more or less the picture is the following. You have your manifold. If you remove a compact set, then you see at least 2 unbounded connected components. It means at least 2 ends. You may think exactly 2 ends if you want. Well, then you have the same conclusion with the factor which is compact now. You have the same conclusion, so M splits as n times r, and n is also compact in this case. Okay, not too important anyway. Why so? Why is it a corollary? It is a corollary because whenever you have at least 2 ends, you can generate a line. How do you do that? You take 2 sequence of points, one over here and one in the other connected components. You connect them with a minimizing geodesic, then you move the 2 points to infinity. And in the limit, you will see a minimizing line, a geodesic. So whenever you have at least 2 ends, you can generate a line, then you apply the main theorem by Chigger-Gromol. Okay, so our result is the following, which is, in a certain sense, a generalization of the corollary. So our theorem is as follows. Theorem with Antonelli, myself, and Shu from last December. It is the following. As always, I'm going to consider the usual setting, so M is always non-compact. So take M, N, G. Okay, whenever I want to stress the dimension, I will put a little n over there. So take M, G, Riemannian manifold, and so on, with at least 2 ends. And instead of assuming non-negative Ricci, we're going to assume a spectral condition, a so-called spectral lower bound on the Ricci curvature. It is the following, so such that. So the manifold is such that for some parameter gamma, which is strictly less than 4 over n minus 1, so n is the dimension. And for simplicity, let's say, it could be also negative, but for simplicity, let me add greater or equal to 0. It's easier to think. For some gamma, it happens that the first eigenvalue of the following Schrödinger operator, minus gamma Laplacian plus lambda rich, is non-negative. Now I will explain the meaning. With this assumption, we are going to have a splitting result. First, let me explain what it means. That it means the following. So first of all, lambda rich. So this is going to be a Schrödinger operator. Schrödinger operator is Laplacian plus a function. So this is going to be a function over the manifold. And I will refer to this function as the potential of the Schrödinger operator. What is lambda rich? Lambda rich is exactly pointwise the least eigenvalue of the Ricci tensor at that point. Okay? So the minimum among vectors at that tangent space of Ricci VV for V tangent vector with norm 1, okay? And when I say first eigenvalue of this operator greater or equal to 0, I mean the following, so this I write down. So this means exactly, by definition, that if you test, if you test the quadratic form corresponding to this Schrödinger operator, you get a non-negative value. It means the following: whenever you take the integral over m of gamma nabla phi squared plus lambda rich phi squared, you get a non-negative number for any phi c infinity c, for example, function over your manifold m. It means the following. All right. So of course, this is going to be, in general, a weaker condition, right? A spectral lower bound on the Ricci curvature, right? So in particular, for example, whenever gamma is, so this theorem is going to be interesting when gamma is strictly positive. So when gamma is 0 or gamma is even negative, of course, you can continue this chain of inequalities and you discover that Ricci is no negative pointwise and you go back to the Chigger-Gromov theorem, of course. Instead, here we are allowing for some possibly negative values of lambda rich somewhere, but those negative values are compensated by, for example, the eigenvalues of the Laplacian in some sense. And so you get a non-negative spectrum for that Schrödinger operator, okay? So two ends, spectral Ricci positive, this is my notion of spectral Ricci positive, where then not only the conclusion is going to be M splits, but actually, in fact, Ricci is non-negative pointwise in the classical sense. And so in particular, you get the splitting, because then you apply the corollary. So in particular, so hence M splits. M splits isometrically as n times r. Okay, so you actually get pointwise non-negative Ricci. All right, so this is the main theorem. And now I will discuss all the assumptions, and if there is time, I will tell you something about the proof in the end. Okay. So first of all, before telling you something more about mathematics, let me tell you something about the literature. It's important. So important remark about the literature. So the very same theorem. So same theorem. The very same theorem, I have to say, was proved independently in a work by Catino, Mari, Mastrolia, and Roncoroni in the same period, independently. And also, since our works appeared, actually, there have been already some generalizations. And so there is, I want to mention a nice work by Hong and Wang, of this year, where they give a version with boundary, essentially a splitting theorem with boundary of so spectral splitting with boundary. So there is a version with boundary of that theorem, and also it appeared also a work by Jung some months ago, where that is a version for weighted manifolds. Okay, so weighted manifolds. So in practice, the Ricci tensor is replaced by the Bakri-Emery tensor, and you have a weight in front of the Riemannian measure. Okay, the proofs, in particular the first two proofs, share some similarity with ours, but they are actually different, so they are independent, and they are all interesting, I believe. All right, so now we go back to mathematics, and now I want to discuss a little bit the assumptions of our theorem. So first of all, I don't know, maybe if this is the first time that you see a spectral Ricci lower bound, I don't know, maybe it might sound a little weird. So the first thing I want to do is to convince you that it is not a weird assumption. So the first thing I want to say is a remark about this notion of spectral lower bound on the curvature. So an observation about spectral bounds on the curvature, on the Ricci curvature in this case, but also other notions of curvature. Now, before actually going into this remark, let me remind a quick observation, a very classical thing. I want to recall for you the formula for the second variation of the area. Okay, so very, very classical, because it's going to play a crucial role in relation to spectral bounds. So what do I mean by second variation of the area? I mean the following. In general, let's say that you have a hypersurface m n minus 1 inside n, which is, okay, to be precise, m has to be two-sided. So the picture is going to be the following. Maybe the blackboard is the ambient. This is m. Two-sided, it means that everywhere there is a pointwise smooth defined uninormal nu. Okay, so there is a normal nu. If there is a normal nu, I can multiply the normal nu by a function, by a test function phi c infinity c, for example. And this becomes the starting velocity for a deformation, right? For a deformation of my manifold. You get a flow, you get the evolution of m, it becomes mt for time, m0 is m, and so you can take the second variation of the area, right? So you can take the second derivative of the, let me write area of mt at time 0. At time 0, what you get is the integral over m of nabla phi squared. Let's use a plus here, maybe. Yeah, plus h squared minus a squared minus Ricci of the ambient nu times phi squared. Okay? Okay, h is the mean curvature, a is the second fundamental form. So you have this very classical second variation formula. This is going to be related with spectral bound. So let's go back to the question. The question was, what is it the meaning of giving a spectral lower bound on the Ricci curvature? Well, I want to convince you that that condition on the spectral lower bound appears indeed quite spontaneously when you study, for example, minimal surfaces, stable minimal surfaces. Stable is going to mean that the second variation is non-negative for any test function. Okay, and so this is my first observation. Maybe I'll do it over here inside the remark. So maybe, yeah, first observation. The observation is the following. Consider, for example, now a hypersurface in Rn, so the most maybe the easiest situation, even it's not easy many times. And let's say that m is, okay, two-sided, so you have a normal, you can take the second variation two-sided, but more importantly, it is minimal. Minimal means h equal to 0, and stable. Stable means that the second variation is non-negative for any test function, okay? So second variation greater or equal to 0, non-negatively defined. Well, then it is actually easy to see that you have lambda 1 of minus delta plus lambda rich non-negative on that hypersurface M. So this is the Laplacian in M, this is the Ricci tensor in M. So in particular, you get that indeed the Ricci tensor of M is non-negative in the spectral sense with gamma equal to 1, for example, with gamma equal to 1. Okay, so it's pretty spontaneous. Why so? This follows from the inequality given by the second variation. So indeed, non-negative second variation means integral over m of nabla phi squared. Now you have minus. Now, it is minimal, so h is 0. This is the Ricci of the ambient, which is Rn, so it is 0. You end up only with a squared, so minus a squared phi, and we are assuming stability. So this is non-negative. And now you play a little bit with the Gauss equation, which relates extrinsic curvature with intrinsic curvature, right? And so you discover that this is just less than lambda rich of m. So you continue the chain of inequalities, you get exactly, this is for any phi, test function over m. And so you discover that lambda 1 is non-negative, okay? So this might seem an easy observation, but it is actually been crucial as an observation for the recent resolution of the stable Bernstein problem. Resolution of stable Bernstein problem, stable Bernstein. The stable Bernstein problem up to ambient dimension up to R6, okay? Maybe I don't write all the references here, but the point is that it has been exactly by observing that
Sorry.
Yeah.
Maybe I got a bit lost on your assumptions. Why did you throw away the Ricci term on the ambient in that discussion? Are you
over here?
Yeah. Are you just saying?
No, just because the ambient is Rn, it is exactly 0. Ricci.
Okay. Okay. So that's specific to that context.
That's
yeah,
right.
Yeah. Okay,
Yeah. I can be more specific. So in this case, I wanted to present the simplest example. So Ricci of the ambient is 0, so you don't get Ricci of the ambient. This inequality is also non-sharp, to be honest, okay? But it is easier to present, I believe. And actually, you can extend this very statement if you admit, for example, if I replace n here with an ambient having B Ricci non-negative, then you do get Ricci n in the second variation formula. But you can again play with the second variation formula to estimate minus a squared minus Ricci of that ambient, again less than lambda Ricci of m. So for example, this works also if the ambient had non-negative B Ricci in pointwise sense. Yeah.
Thank you.
Thanks to you. And okay, so the stable baseline problem, very famous nowadays, is the problem asking whether a stable minimal hypersurface in Rn up to R6, up to R7 is in fact a flat hyperplane. And it has been solved in R4. Okay, maybe I don't write all the references. It has been solved in R4 by 2 works of Chodosh-Lee and also by a work by Catino, Mastrolia, and Roncoroni. Then in R5 by Chodosh-Lee, Minter, Stryker. Then in R6 by Mazet after a crucial contribution, I want to say, by Antonelli and Shu. And the point is that if you read the papers, in many of those papers, it is crucial to pass through this observation. All right. So this was the easiest situation where spectral bounds come up. But I want to make a second observation. Maybe it's, so I would like to point out that somehow spectral lower bounds on the curvature were already present in very classical, very famous, very important works in some sense, even if they were not mentioned. For example, I want to point out the following example, if you want, where implicity already appeared non-negative, lower bounds in the spectral sense. It is about the Garrosh conjecture, the example I want to make, a Garrosh conjecture. Garrosh conjecture, which was proved, so it's now a theorem, was proved by Shen Yao, Yao, and 79, and also by Gromov, Lawson, and 80. All right. And the Garrosh conjecture, anyway, was the following conjecture. It stated that there are no metrics G on the n-dimensional torus such that the scalar curvature is strictly positive pointwise on T. So there are no positive scalar curvature metrics on the torus for any n greater or equal than 2. Also 1. This was the conjecture. And somehow, in particular in the proof by Shen Yao, I want to convince you that somehow spectral lower bounds on the curvature were already present. So this is, in other words, another perspective on spectral lower bounds. So okay, I think we remember Chigger-Gromov theorem. And you know, in Shen Yao's proof, they use the following tool. Maybe you are very familiar with it. There is the following tool. They use a so-called slicing of the manifold, slicing of the manifold by area minimizing surfaces, k-dimensional surfaces. I will call surfaces. Area minimizing, area mean surfaces. In the following sense. You start from your ambient, which is the n-dimensional torus, and by some argument related to GMT, you can find a hypersurface, which is area minimizing within its homological class. So in any case, if you just perturb it, the area increases, okay? Then they are able to iterate this procedure. They will find an n-2 dimensional hypersurface in size the previous one. You go on, you get this sort of slicing, and you end up with a final 2-dimensional surface sigma 2. And what happens? What happens during this procedure? These are area minimizing. If they are area minimizing, they are stable. They are minimal, okay, and they are also stable, right? So they have second variation for the area greater or equal to 0. Let's apply again this the fact that the second variation is non-negative in this case. For example, for the first hypersurface, you get 0 less than, this is the stability condition, integral over sigma n minus 1. This is an n minus 1. Sigma n minus 1. Nabla phi squared, phi is the unit test function, minus a squared. H is 0 because it is minimal. And now you do get, in general, plus Ricci of the ambient, which is the torus now, Ricci of t, nu phi squared, for any test function phi in sigma. And again, this is the crucial observation by Shane Yao. It is the fact that you can play again with the Gauss equation, and you discover that you can estimate from above the curvature term by the following quantity. Again, this is not going to be sharp, but easier this way for the moment. You can estimate this from above by 1/2 scalar curvature of the hypersurface minus 1/2 scalar curvature of the torus. Okay, so everything is multiplied by phi squared on the right-hand side. So now you know the proof. Actually, Shane Yao's proof goes by contradiction. So imagine if, for example, the scalar curvature of the torus were by contradiction positive at any point. I could actually make by compactness a positive lower bound. Okay, you know you can. So let's, for example, put beta greater or equal than beta greater than 0. So scal t. This is you have a minus in front. I am also taking the minus here. You put the inequality inside the chain of inequalities. You are going to get that integral over sigma n minus 1 of beta over 2 phi squared is going to be less than integral over sigma n minus 1 nabla phi squared. There is a plus 1/2 scalar sigma phi squared. Okay, so you get that other lower bound. But what do you recognize here? What do you recognize? You recognize that this is a bound from below on the first eigenvalue of another Schrödinger operator. So in other words, you could say that lambda 1 of minus Laplacian plus 1/2 scalar is greater than beta over 2. Greater than beta over 2. So in this case, you have a positive lower bound in the spectral sense on the scalar curvature, if you want. And an important observation is that you know, this basically the same lower bound you had for the ambient is preserved when you pass to the hypersurface. That's the key observation. And another point is that, so this is something present in their work, but it is not this observation that they need. They use this observation to imply that, you know, the PDE for solving the conformal Laplacian equation has a solution. And so you can turn the fact that you have this inequality in the fact that the metric on sigma is conformal to a metric with positive scalar curvature, having that lower bound. So you translate the information in this way, but you do pass through the fact that you have an eigenvalue greater than beta for a notion of curvature in a spectral sense. So I see this similarity, for example. And now we arrive to the final crucial observation I want to make in this remark. The final crucial observation is the following. So you may have noticed that in this remark I am turning the information that I have a hypersurface that is area minimizing. I am turning that information in saying that that hypersurface has a lower bound in the spectral sense on a notion of curvature. Okay, but in this remark, I never really used the fact that the hypersurface is area minimizing, but rather the fact that the second variation of the area is greater or equal to 0, just stability. I'm using essentially stability, not really area minimizing. And so the third observation I want to make is that, in fact, we can exploit this observation, developing a new tool, in particular developed by Gromov, starting from Gromov 96, which is the idea of using, instead of area minimizers, using mu bubbles, so-called mu bubbles, in place of area minimizing surfaces, hypersurfaces, and so on. What is it, a mu bubble? Well, in general, if you want a sort of definition between quotes, the definition is I will call a mu bubble any minimizer, any set. It's going to be a set, but we will focus on the boundary of that set, of course. So a mu bubble is going to be a set E such that it is a minimizer of, if you want, E mapped to area of the boundary plus a volume term, integral over E of some weight h, function that I will choose depending on the problem, okay? So I'm still asking for the existence of a minimizer, but now it is a minimizer of perimeter plus a volume term, perimeter plus a volume term. But the idea is that if I do get a minimizer of perimeter plus a volume term, then I can compute the second variation of this other function, which is no longer area plus something. But again, if it is a minimizer, it's going to be stable for the second variation of that operator. And then if H is chosen properly, then maybe I will turn this non-negativity of the second variation for that operator into a spectral lower bound on the curvature. This is the crucial observation, okay? And there are many advantages of this, but I mean, maybe in some cases it is more convenient to use area minimizing surfaces, but one possible advantage is that finding area minimizers sometimes it is difficult. For example, in the previous case, one ensures the existence of those sigma by topological arguments because the torus has a lot of topology, namely, yeah. Indeed, yeah, no, just a name, mu. But everybody calls them mu bubbles. The reason is that I believe that the reason is that Gromov in the original paper put mu here in place of H. So everybody calls them mu bubbles, okay? So this is a mu bubble, even if there is no mu, indeed. Okay, so I was saying maybe by cooking up a suitable H, it is easier to construct a minimizer of this functional just by direct method in place of proving existence of area minimizing surfaces, which maybe requires topology. And indeed, just to draw a connection between classical works and maybe a very recent one, I want to point out that this idea was, for example, used in many recent papers, but for example, in a paper by Chodosh Lee, published last year, where they proved that if you have an n-dimensional manifold, this time compact, this is the only time I stress compact, otherwise my m's are always non-compact, compact with dimension less than or equal to 5, which is aspherical, so such that the universal cover is contractible, well then you have no matrix on M with positive scalar curvature, on M with scalar curvature strictly positive, okay? And if you look closely at this theorem, this is exactly, in some sense, a generalization of the theorem about the Garrosh conjecture, right? Because the universal covering of the torus is Rn, which is contractible. In this case, I'm not assuming I'm not assuming anything, okay, it's not true, but about the compact manifold, I'm assuming that the universal cover is contractible, and in that case, I prove the same conclusion. You have no matrix with positive scalar curvature, okay? And in that, by the way, the same theorem was also proved by Gromov independently. And they developed exactly a slicing by mu bubbles in place of a slicing by area minimizing hypersurfaces, because they don't have a topology a priori in M, right? Okay, good. All right, so this was to give you some intuition about spectral lower bounds on the curvature, and this was the observation about the crucial assumption in our theorem. In our theorem, we have two more assumptions. One is the fact that I am assuming two ends, and the other is a specific range for the parameter gamma, okay? Now I want to point out that in some sense, both assumptions are needed, are sharp in some sense. Okay, guess I can erase this one now. So, final remark about assumptions. Remark about assumptions. Remark about assumptions. Okay, so let me start from, okay, again, a quick observation, which is again classical, like the second variation I mentioned before, but let me start with this observation. The observation is, there is a useful way of, for rewriting this condition on lambda 1. Lambda 1 of minus gamma delta plus lambda reach greater or equal than 0, well, this is equivalent to say that there exists a function u in C2 alpha of the manifold such that U is strictly positive pointwise, and it solves basically the Euler-Lagrange equation for that Schrödinger, for that quadratic form. So minus gamma delta U plus lambda reach U greater or equal to 0 pointwise everywhere, okay? This is an observation following by the classical work by Fischer-Kolb-Richain from 80. Okay, so many times, so these are equivalent, okay? So if I can exhibit a function U as on the right, then I get that lambda 1 greater or equal to 0. And I will exploit this observation. So let's go back to the assumptions. So first observation about assumptions, in particular about the range for gamma. Gamma less than 4 over n minus 1 is a sharp interval, is sharp. So if you assume the same assumptions with greater gamma, you don't get, in general, splitting, you don't get reach greater or equal to 0. The counterexample is the following. You can take mg to be just 0 plus infinity times torus n minus 1 endowed with the hyperbolic metric. So I'm going to call t the variable on the line, half line. So you have dt squared plus flat metric on the torus, so standard flat metric on the torus, flat over t squared. So basically, what I'm doing is I'm considering the hyperbolic space. Think of the model, the half space model, and then I am taking the quotient with respect to okay, I'm taking a quotient like that to turn the hyperbolic space into a product 0 plus infinity times torus in the other n minus 1 dimensional directions. Okay. So in particular, this is a quotient of the hyperbolic space, so it has constant sectional curvature. I can compute the Ricci pointwise. The Ricci is going to be negative. It's going to have two ends, because if I remove a compact set here, these are two ends, of course. The distance from a compact set to this line is plus infinity, of course. It's complete. And so you have two ends. You know the Ricci curvature exactly, but you can also compute the first eigenvalue of minus Laplacian, just like if you computed it on the hyperbolic space. You compute it and you get n minus 1 squared over 4. Okay, so if you want to be precise, you get this lambda 1. And so in particular, this implies that whenever you take gamma greater or equal than 4 over n minus 1, you discover that lambda 1 of minus gamma delta plus lambda Ricci, this is greater or equal to 0, exactly by plugging in the Ricci curvature of the hyperbolic space and the fact that you know lambda 1 of the Laplacian. For this gamma, you get this is not negative, but clearly this doesn't split. It doesn't split. It has no Ricci greater or equal to 0 pointwise. So you have a counterexample for higher gamma. So okay, fine. I mean, gamma is sharp, but maybe it is more interesting. Maybe, in my opinion, it's more interesting to know that also the topological assumptions about two ends, so the two-endedness, so greater or equal to ends, is a necessary assumption in some sense. Is somehow, I mean, if you don't want to assume anything else, is somehow necessary. Necessary. In the sense that, you remember I erased the classical Cheeger-Gromov theorem, but the classical Cheeger-Gromov theorem didn't ask for the existence of two ends. The classical Cheeger-Gromov theorem asked for the existence of a line. So what I mean in the following observation is that the line version of the spectral splitting theorem is false. So we really needed to focus on the two-ended, on the generalization of the corollary, not of the theorem. So the point is that the line version, let's call it line version of Cheeger-Gromov of splitting, is false in this case. Is false in this case, of course, in this case, not false for them, false in this case. Because you can consider the following example. I'm going to take just a perturbation of Rn. You take Rn with the delta is the flat metric, the identity, that is the flat metric, and I add epsilon g, where the support of G is, for example, compactly contained in B1 alpha in the Euclidean sense. Okay, so basically I'm saying consider Rn. This is Rn, and inside, if you want a tiny ball, you perturb a little bit the metric there. Okay. Also, for this example, I need n greater or equal to 3. This will be clear in a minute. And you see, in this example, if you just perturb the metric here in a neighborhood of the origin, if you consider a Euclidean line very far from the origin, this is going to be, again, a line for the new metric delta plus epsilon g by triangle inequality, essentially. And but yet, I want to point out that if epsilon is sufficiently small, then lambda 1, my eigenvalue, my least eigenvalue, is greater or equal to 0. But of course, if I choose g randomly, you don't get the splitting, okay, along the chosen line. So you don't get the line version of the splitting theorem. And I am going to exploit the observation here. Instead of proving lambda 1 greater or equal to 0, I am proving the existence of a solution here for the Schrödinger operator. And I can do this only for n greater or equal to 3. So to be honest, I don't know what happens in the case n equal to 2. And the idea is the following, that if n is greater or equal to 3, then the green function around the origin looks like that. This is the green function, okay? And for example, if you consider radius equal to 1 around the origin, I can truncate smoothly this function, and I can add a strictly concave cap over there. I get a smooth function u, if you want, a smooth function u, which is strictly positive everywhere, So this is the first requirement there, and also with the following properties, such that if you computed the Euclidean Laplacian of u, this is in general greater or equal to 0 everywhere, and the Euclidean Laplacian is going to be strictly less than 0, for example, in B1, in the unit ball. Okay, and so now if epsilon is sufficiently small, considering the fact that the perturbation is only in a ball of radius 1/2, so the Ricci of the new metric is still 0 outside the ball of radius 1, okay? For epsilon very small, delta also with respect to the perturbed metric is going to be negative inside B1, is going to compensate the fact that I'm changing a little bit the Ricci inside B1/2, okay? If you do the computation, you can show that these properties imply that U indeed satisfies the inequality for any gamma. So the idea is that for any gamma positive, there exists epsilon sufficiently small such that this U solves the greater or equal sign in this inequality. All right. Okay, so this is about the assumptions. Now, in the remaining time, I would like to tell you something about the proof, which I hope it will be sufficiently easy to to explain. Okay, I will cheat a little bit. So if you look for the article, you will not find exactly what I write, but cheating, I think it's good here to explain. So some words about the proof. So the proof is based on two main ideas. So one idea, we already said it. One idea is that maybe finding area minimizers or mu bubbles, in fact, we will construct mu bubbles. Finding area minimizers or mu bubbles is a way to test the manifold, to test the ambient manifold M, okay? So to see what happens inside. This was hinted by, for example, Shen Yao's proof of the Garrosh conjecture and so on. So we already discussed this idea, but it will be not enough to just show existence of a mu bubble. It will not be enough. We will need to construct an area mu bubble, actually. We will need to place mu bubbles exactly in a specific location, okay? So we will combine this idea with the second idea. The second idea is, I will call it a sort of surface capturing technique. This is also not a brand new idea, okay? I want to maybe I don't have time to exactly describe you an example, but just let me mention some people. This will be a technique for placing my mu bubbles where I want. This was applied in the case of area minimizers, for example, in the work by Gang Liu from 2013 that implied the Milnor conjecture in dimension 3, but also by Carlotto Chodo-Scheik-Meyer in the work in 2016 to prove that if you have an area minimizers in a three-dimensional asymptotically flat manifold with a negative scalar curvature, then that is actually R3 flat. Okay, so indeed you get a sort of splitting in the end. So we're going to combine these two ideas. Okay, no. So let's move to the proof, the actual proof. So we are assuming that lambda 1 is greater or equal to 0. Fine. So in particular, because of an observation I wrote before, I can use Fisher-Corby chain observation, I can fix u0, a function such that minus gamma Laplacian u0, a specific function, plus lambda rich u0 is pointwise greater or equal to 0 on my manifold. This is, right, this is observation, a translation of the assumption lambda 1 greater or equal to 0. Good. Fix u0. The picture is something like this, the picture. My manifold has two ends, so something like that. If I remove a compact set, I get two unbounded connected components. Okay, so the picture of M, something like that. Fix a point x. My goal, my final goal, is to prove that nabla u0 at x is 0. Why so? Because x is a generic point. If I prove that, then u is constant. Gradient is 0, u is constant. If u is constant, the Laplacian is 0. But then u is a positive constant function, so u is like 1, and lambda rich is greater or equal to 1, which exactly means rich greater or equal to 0 pointwise. Okay? So my goal is to prove the gradient vanishes at a specific point, which is generic, and then u0 is constant, then rich is non-negative pointwise. Okay, now I need to tell you about the construction, so now something more technical. I said I have two ends. If you want, as an exercise, you can prove that, for example, you can call omega naught, this is omega naught, for example, a specific end. And also then you can consider the distance function from the boundary of omega naught. You take the distance positive on one side and you go to plus infinity. You take minus the distance, this would be the sign the distance function from the boundary. Okay, and you go back to minus infinity. So essentially, let me say it like that, you have kind of an axis running from minus infinity to plus infinity inside your manifold, considering the distance function, okay? If it is the distance function from the boundary of omega naught, the 0 of this axis is exactly where there is the boundary of omega naught. Okay, so let's say that there is this coordinate running inside my manifold. Okay. Also, if you move everything in the correct way, for example, you can place omega naught so that x, for example, falls. So let's say that x falls between -1 and 1 for this line. Okay, you can do that. Okay, good. Now, the first idea, which is not the point here, is that you can modify, if you want, and also fix a little radius here around x inside that -1, 1. So I was saying the first idea is that you can modify u0 in the following way. You take u0 and you turn it in a new function, u, which is just u0 plus aw, where a is positive, a eventually is going to 0, so u goes back to u0, okay? And w is another function, and what is the property of the new function u? The new property is that this is such that minus gamma Laplacian of u plus lambda rich u is still greater or equal to 0 on m minus br centered at x, but you can in general push up a little bit this lower bound, at least on a compact set. And you can do this in the following sense: minus gamma delta u plus lambda rich u is greater or equal than some number mu, depending on a, strictly positive, for example, on a compact set, on that slab -1, 1 minus br. Okay, so now I will repeat. So this is, I'm sorry, the technical part. This is not a big surprise. So this is just a PDE argument that produces a perturbation of W, okay, a perturbation of U naught by a function W. You add a multiple of that W to U naught, and basically you can increase a little bit this lower bound, but outside the ball BR. That's the point. You can do that only outside the ball BR. And outside the ball BR, you still have greater or equal to 0. But just by continuity, for example, in -1,1 minus BR by compactness, this is going to be greater than 0, then I can fix a constant, a positive lower bound. I call it mu A because it depends on A. Strictly greater than 0, at least in this region, -1,1 minus the ball. Okay, so you push up the curvature a little bit in this spectral sense. Okay, and now we want to, for some reason, we want to place an area minimizing surfaces, or rather a mu bubble, as close as I can to X. Why? It will be clear later, but okay, I want to place a minimizer close to X. How do I do that? I want to build a mu bubble, so I need a weight. And the weight, H, is the following. I'm going to consider two more numbers here. -1 over epsilon. Epsilon eventually goes to 0, so -1 over epsilon is really on the left, and 1 over epsilon is instead really on the right. Okay? And let me draw the one-dimensional profile of that function h. The function h is going to be 0 where there is 0. It's going to plus infinity on the left. It passes through 0 and goes to minus infinity. This will be my weight h epsilon that I will put inside the functional for the mu bubbles. This is also a very typical choice to use this kind of tangents, cotangents function. Indeed, you can build this h epsilon by combining two hyperbolic cotangents, okay? And by the way, this is already an idea by Jintian Zhu of a couple of years ago to use this function. This function has a couple of nice properties, and maybe I will write the properties over here. This is really calculus to prove that that combination of cotangent, hyperbolic cotangent functions, that function has a couple of nice properties. Let me write the properties like here, okay? We will need two properties. This is the lab -1,1. This is lab -1 over epsilon. So this is a 1. This is 1 over epsilon, okay? If epsilon goes to 0, this function goes to 0 smoothly on compact sets, okay? It becomes very, very flat. And so in particular, inside the slab -1,1, you can say that we will need this quantity, h prime epsilon plus h epsilon squared. This is less than epsilon inside up to constant, inside -1,1. And instead, in the other two slabs, so inside here, you have a nice inequality on that thing there. H prime epsilon plus, this is a minus, sorry. H prime epsilon minus h squared epsilon is going to be strictly less than minus epsilon. So you gain something. You gain something outside the slab -1,1. It's really less than minus epsilon. Okay. Okay, so this is the, I'm sorry, it's a bit technical now, but this is the setting. Now we are ready for the proof. Now I can build my mu bubble. So yeah. No, not yet. I'm going to use it soon, but I mean, this is just a one-dimensional function, h epsilon. It just stays there. No, not even there. No, there you just use the non-negativity of the eigenvalues for a Schrödinger operator to solve a PDE. So it's just to solve a PDE. No, just the gamma is positive if you want. I'm just using gamma is positive. Gamma could be 10. Yeah. All right, so now we take our mu bubble. So minimize. I want to minimize the functional that takes a set. So minimize. So you take infimum of. Also, a natural choice here. Since my ambient has not a pointwise lower bound, but rather a spectral lower bound, a natural choice in the literature is not to minimize area plus volume, but weighted area plus weighted volume, okay? And the correct choice for the weight, so instead of writing the measure of the boundary of a set, I'm going to weight the boundary. And the natural choice is to use your function raised to the power gamma. This is the right choice in this case. And notice I'm taking u, not u naught. I'm already playing with u. And then the classical choice is to subtract the volume integral. The volume integral, don't focus too much on what I'm writing now, is characteristic of E minus characteristic of omega naught, U power gamma, H epsilon, among all the sets E whose symmetric difference with omega is compactly contained in my slab minus 1 over epsilon, 1 over epsilon, okay? So among all possible perturbations of omega naught is kind of my reference set. Perturbations that are contained in the larger slab, I want to minimize weighted area plus weighted perimeter, and there is this difference of characteristic functions just to make that the perturbation is positive. I am adding a positive term, okay? In your mind, you can delete this characteristic function and say, okay, I am adding a volume term that has a weight, okay? All right? And you're gonna get a minimizer. So by direct method, there exists a minimizer which depends on epsilon. I'm calling it omega epsilon, my minimizer. Okay. And now we said the whole point was when you have a minimizer, you expect you will find some information by computing the second variation, because the second variation is non-negative because it is a minimizer. You compute the second variation. You compute the second variation of your functional, and you get the following estimate. You test, you remember? A good idea for testing the second variation, for example, is to use a test function phi equal to 1. I didn't tell this before, but it's very classical to use phi equal to 1. In this case, in place of phi equal to 1, a good idea is to use essentially a function that is similar to u to the power gamma. So now you can test the second variation with test function phi equal to, there are many choices. One choice is u to power minus gamma over 2, if you want to know. And then you get an estimate. The estimate is going to be 0 less than something, because this is second variation, non-negative, okay? Now, up to a multiplicative constant, and here I'm using the gamma less than 4 over r minus 1, otherwise you don't get this upper bound, okay? So you compute the second variation, you do a couple of computation, 0, because stability, is less than integral over the boundary of omega epsilon of minus gradient of u, and you have the full gradient, the gradient on the ambient of u squared, plus that strange difference I had before. It appears, this strange difference, h prime modulus minus h squared, okay? You have that strange difference. And then you have your PD minus gamma Laplacian u plus lambda rich u. That's the point. That's the point. You exploiting the assumption gamma less than 4 over n minus 1. You can stability turns into this bound. We have 3 terms. This is just a non-positive term. We will go back to it later. Then you have this strange, it is inevitable. You will get some derivative of h because it is in your function. You get this strange sum for h. And then you have basically your PD. Notice I have put a minus here. All right. And now I want to show you that the boundary of omega epsilon is very close to x, which is what I want. I want to build a mu bubble passing very close to my favorite point x. And the point is the following. First observation, we are going to play with the same observation twice. First observation, I claim that boundary of omega epsilon, which could be everywhere in the large strip minus 1 over epsilon, 1 over epsilon, at least I can tell you that it intersects the slab minus 1. The slab minus 1, 1. This is already similar to an observation of Ju that I mentioned before. And why so? Because, think, if by contradiction, your boundary doesn't intersect the slab minus 1, 1, it would mean that the boundary would be, for example, somewhere there, boundary of omega epsilon, outside the slab minus 1, 1. But then you get a contradiction, because outside that slab, you remember, you have that the strange sum is strictly less than minus epsilon. So you get less than or equal to 0, less than or equal to 0, and less than minus epsilon. 0 less than minus epsilon. Impossible. So it is not true that it is completely outside here. It must intersect minus 1, 1. After I know this, now I do the same observation again, and I claim that boundary of omega epsilon in fact intersect the little ball around X. Why so? Because if by contradiction this is the case, so you do intersect minus 1, 1, but by contradiction you don't intersect the little ball, then what happens? Again, look at that at the formula. Imagine the formula, for example, intersection minus 1, 1. What do you get from that formula? Otherwise, what you get is 0 less than, the first term is non-positive. The second term is bounded by epsilon. It's bounded by epsilon, just by smoothness, so it's less than epsilon area of the boundary inside minus 1, 1. And the final term, if by contradiction I'm saying I don't intersect the little ball, then I have a strictly positive lower bound on the final term. Okay? So for the final term, I get minus mu a area of boundary omega epsilon intersection minus 1, 1. Okay? And remember, I first chose a, and epsilon is free. So this is true. This is going to be true for epsilon, let's say, smaller than mu a. For epsilon smaller than mu a, I get that this is strictly negative. This is strictly negative, and I get a contradiction. So once again, this is not the picture. The picture is my surface intersects the little ball. Actually, I'm capturing the surface towards the point X. All right, and now you do the limits and you are done. In which sense? So conclusion, if you want. Right here, the conclusion. Conclusion, now you take a sequence. You let A equal to AI going to 0. This corresponds to mu AI going to 0. For any I, you choose epsilon I less than mu AI, so going to 0 again. And when you pass to the limit, you're going to get a sequence here of boundary omega epsilon I. Boundary omega epsilon I is going to boundary of omega, I don't know, boundary of a set U, final set U. And the point is that boundary of U still intersects BR X, because the whole sequence used to intersect that ball. So this is different from the empty set. And when you pass to the limit, the inequality, for sure, you get 0 less than, up to constant, integral over boundary of U minus nabla mu squared. And since I passed also A to 0, U goes back to U naught, right? So I get a hypersurface now. Eventually, it's going to be an area minimizer a posteriori. It passes very close to X, and it satisfies this inequality. Okay? But so in particular, the gradient of U naught is going to be 0 over the boundary of U. Let's say that now this is the boundary of U. So you discover that the gradient of U naught is 0 over the boundary of U, so it is 0 on a point close to X. You let R to 0, you discover that the gradient of U naught is 0 exactly at X, which was my initial goal. Okay, this completes the proof, and oh, sorry for the overtime. Thank you very much for your attention.
Is there any question?
Just a technical detail. In passing to the limit there, so you convinced me that you can somehow constrain your domain to go through a pre-assigned ball, geodesic ball around X. There's a technical point in understanding how that convergence happens. So I didn't read the paper, unfortunately, but I was wondering whether you are going through the standard path, which would be claiming area bounds and bounds on the second fundamental form, or whether a priori you have less information and you're going to take a weaker limit, because it seems like you need the whole machinery, because you're even passing the inequality to the limit. Mm-hmm. So somehow just going through GMT perspective is not quite enough, and also given the fact that your function is pretty complicated, it's not super clear to me. And also you are claiming it in all dimensions. So I wonder how you handle the second fundamental form term. Yeah, thank you.
Okay. Okay, no, thanks for the question. Yeah, I skipped this part in the talk, of course. No, I don't claim I have smooth convergence, indeed. So I am claiming everything is smooth, but it is not. So I'm just using pre-compactness of sets of finite perimeter locally around a point. Now, I also use a couple of, so a priori, I just have convergence in the sense of set of finite perimeter, which is very weak. In the end, I can discover that my limit set U, okay, is going to be a minimizer for a weighted perimeter, because when epsilon goes to 0, I will get a minimizer for integral over the boundary of U to gamma, okay? Because H disappears in the limit epsilon to 0. So I get a minimizer for a weighted perimeter. So I can use the classical theory to say that at least up to a codimension 8 set, my boundary is at least C1, okay, let's say smooth, okay? And also, you can prove for such sets uniform density estimates. So the perimeter converges as a measure. So as a measure. So this integral passes to the limit. I do get this inequality over a boundary which is smooth only outside a set of a very small set in house of dimension sense. So at least close to X, I find a regular point for the boundary of U where I mean this integral is meant in a classical sense, if you want, and so the gradient there is 0, and in any case, it is any point very close to X. So there is this part where you need the classical regularity theorem, and density estimates. But this is the combination of these two tools, I would say. No, it's not cheap. Oh, well, actually, not. You can rely on classical facts for this, very classical facts. So we didn't prove this part. You can rely on classical facts, definitely.
Maybe a naive question. So for your main result, if the manifold is a weighted manifold is a similar spectrum non-positive implies the Buck-Emery curvature non-negative result?
Well, what I was saying before is that there is this other work by Young, okay?
Okay.
He proved, if you want, the very same statement where you replace lambda reach with lambda Buck-Emery corresponding to a given weight in front of the volume measure for your manifold.
Using
okay?
the
You take a volume. Huh?
Using the similar technique.
Yeah, very similar technique. That paper is very similar to ours. The other two are a bit different, I have to say. Yeah.
Okay, thank you.
Thanks to you.
Actually, I have a question. Would it be feasible to expect some kind of rigidity in the borderline case, gamma equal to 4 over n minus 1, like also view of your example, which is quite special, maybe like a Killing vector field or so?
To be honest, I don't know. So the true answer is I don't know. But I don't have counterexample to the following statement. Maybe there is a range running from 4 over n minus 1 maybe to a larger number, where maybe instead of getting an isometric splitting, you get a splitting as a warped product.
Yeah.
That is possible. But I don't know how to prove it. I don't have counterexample. This is just an, I don't know, a fantasy. Okay. But it is possible. I mean, I don't have counterexample to this.
All right, so I guess we can thank Marco again.
Thank you very much.
So welcome to this afternoon session. The first speaker of this afternoon is Giada Franz from Université Gustave Eiffel, who will speak about unknottedness of free boundary minimal surfaces and self-shrinkers.
Thank you. Thank you for the introduction and for inviting me. I hope you can hear. It's always nice to be back to Pisa. In this same room, I was taking my first classes in Riemannian geometry with Andrea, so it's nice, always nice to come back. So yeah, I will talk about unknottedness of these two objects, free boundary minimal surfaces and self-shrinkers mainly. So I will start by giving the introduction, definitions, historical background, and statement, and hopefully I will be able to give a sketch of the proof. So let me start right away saying, where does this unknottedness problem come from? So there is this paper of Lawson in 1970, where he studies minimal surfaces in the sphere, three-dimensional sphere, and he proves that every minimal surface and I mean, in all of the talk, I will talk about very smooth, embedded, nice objects. So smooth, embedded, and in this case also compact. In some other of these cases, self-shrinkers will also be non-compact, but in this case compact, is unknotted, sorry, in the three-dimensional sphere, S3, is unknotted. Meaning that if you have one of these minimal surfaces, there exists an isotopy that brings it to a model surface with the same topology. So I will draw a picture in a second and it will be clearer, but by unknotted here, I mean that there exists an isotopy of S3, so an ambient isotopy, mapping the surface to a model surface of the same topology. What do I mean? So, for example, for genus G equal to 1, so if you have a surface of genus 1, and here I'm really talking about two-dimensional surfaces. So if you imagine this torus embedded in S3, this is okay. So this can be a minimal surface. But for example, if I have a tubular neighborhood of a trefoil, then that's not okay. And I always have problems drawing this. But so let me look at the picture, otherwise it takes a while. Here. So you can intuitively, this is knotted, this is unknotted, this is a knotted surface, okay? So there's not exist an ambient isotopy that brings this into this one, okay? And actually, this is the same paper, where Lawson states the Lawson conjecture, stating Lawson conjecture. So for genus equal to 1, we now know that the only minimal surface in S3 that has genus 1, that is a torus, is the Clifford torus. Okay, so stating that Lawson's conjecture, which is exactly there exists only one minimal surface of genus 1 in S3. Now, this is proven by Brendle. At that point, it was not known. And all what he proved is that, okay, at least it's unknotted. Okay. Great. So it's very tempting to try to consider the same question in different settings. So let me try to put all together here. So we just stated like minimal surfaces in S3. Okay. So let me see if they can all fit here. Maybe. So as I said, here, what's minimal surface? We have the sphere S3. Okay, let me draw in one dimension less. And I have the surface inside sigma. So minimal surface is just mean curvature equal to 0. And then we said, okay, if we have a minimal surface, it can be ambient. There exists an ambient isotopy with a model surface of the same topology. And in this case, the topology is just the genus. So I have to check the genus, and I know how it's displaced, let's say, inside S3. And this, as I said, is Lawson in 1970. But then, okay, another very classical setting that most of you have studied partially at least is minimal surfaces in the Euclidean space, R3. So we know the case, for example, the catenoid. Okay. So again, we have now complete, non-compact, possibly, but always smooth embedded minimal surfaces inside R3. Here, the topology is a bit more complicated. So given, but again, they are noted as is true. So given any minimal surface, such like this one, we can isotope it to a model surface with the same genus and the same number of ends. So as like we saw in the previous talks, number of ends is like if you remove a compact set, how many connected components we have that go to infinity. And the unknotedness in this case, very similar statement, was proven by Xiao in the 92, around 92, and Froman Mix as a generalization also with like infinite topology, but will not enter into that. Just want to state some literature. Okay. And then, well, I mean, there are many other different cases where you can study minimal surfaces. The two that we were interested in with Sabine, actually, yeah, I didn't say all of this is joint work with Sabine too, were these two free boundary minimal surfaces, minimal surfaces in B3, and self-shrinkers in R3. So let me say very briefly what are these objects. So free boundary minimal surface in B3, we just have the three-dimensional unit ball. And we consider surfaces inside that potentially have some boundary. For example, this equatorial disk. So we have sigma inside B3. And we ask for surfaces that have mean curvature equal to 0. So they are minimal surfaces, but they also intersect the boundary orthogonally. So sigma intersect the boundary of the ball orthogonally. And again, they arise variationally naturally because they are critical points of the area when I also move the boundary. Okay. And here again, we wondered about unknotedness to understand what they can be isotoped to. We have to understand the topology. Here again, we have two parameters, a genus and a number of boundary components. And actually, a variant of the unknotedness result was already proven by Choi Fraser in 18. And well, we extend this slightly with Sabine. And maybe I will describe in a second the ingredient that is that we introduced, but basically the unknotedness was already here. Okay, so now then we have this case here of self-shrinkers in R3. Again, we can see this. So self-shrinkers, probably many of you know, arise as singularity models for mean curvature flow. So if you do a blow up in a certain way in a singularity of the mean curvature flow, you get self-shrinkers. If you are flowing surfaces in three-dimensional objects. But from the point of view of minimal surfaces, they are actually minimal surfaces in a certain space. So in R3 with the Gaussian metric, so e to the minus x squared divided by 4 times the Euclidean metric. So this is the Gaussian metric. And with respect to this metric, they are just minimal surfaces, okay? And in this case, again, let me write, the topology is, again, they are complete minimal surfaces embedded in R3. So the minimal surface, we are basically in this same case, the topology is identified by the genus and a number of ends. And okay, there were partial results by Mramor and Mramor-Wang, proving unknotedness also in this case of these objects, and we extend it to the general case. So this is basically what I want to talk now in a bit more detail. So this is like the summary, but I will also give a general, so a statement, a precise statement. Yeah, sure. Yeah. That's right. Yeah. I think you can also define it in another way, like well, yes. Yeah, let's say yes. There's probably also another way of stating annotation, but this is the easiest one. Yeah. Okay. And I will show you. Well, maybe not. Maybe some of the cases I will show you. I think you can think for this one, for the compact things, they are just the isotope to the standard standardly embedded genus G handle body. So, and if you have boundaries on hands, you just attach hands and boundaries very naturally. So, okay. So let me do a brief remark. Actually, so here I consider cases in very nice ambient manifolds. You can generalize this a little bit to more ambient manifolds. So results all more in general. In ambient manifolds with some positive curvature condition of some kind. For example, positive Ricci curvature. This kind of problem has been studied also trying to relax this assumption. But actually, if you relax it too much, you can have knotted minimal surfaces. So there are examples of knotted minimal surfaces in the hyperbolic space. And this is result of De Oliveira, Sore, also in the 90s. So we need some positive curvature assumptions. Okay, but okay, I stated very roughly, but what does unknottedness mean? Which goes back to what you're saying, to your question. What does unknottedness mean more precisely? In particular, in these two settings. In the settings with the star. Okay. Okay, so the problem is that we have the following two examples. So consider the following two examples. Of free boundary minimal surfaces in the ball. So people maybe maybe they fit. So there are really many examples that people try to construct of these objects, and the point is that there are really many, but there's some sort of rigidity also. But okay, what has been constructed? For example, they are these two. So one that look like an equatorial disk, the one that I drew before, and a portion of catenoid, okay, untouched in some way with some topology in the middle. And the other one, same topology. So this has some genus, G, and 3 boundary components. Okay, 1, 2, and 3. Another example with the same topology is this one. So the 3 boundary components here, they're kind of stacked, one on top of the other. Here they are sort of, not stacked. And there's some genus in the middle like that. So here is again genus G and 3 boundary components. So these are this one well, there are similar constructions by other people, but probably the first one is by Kapuleas-Lee of this one. And this one by Karpukin, Kuzner, McGrath-Stern. Oh. So here it seems there's a problem because these have the same topology. They are surfaces with the same topology. So what we would like to prove unknottedness is that there exists a model surface such that both are isotopic to this model surface. But this is not possible because if we just look at this potential isotopy on the boundary, then you see the boundary components here are one stuck into the other one are disjoint, but an isotopy that has to preserve this property. So these two are not isotopic. So this go back a bit to what is the model surface. And okay, okay, I said that we prove some sort of unknottedness, but this is not exactly just with genus and number of boundary components. So what's the problem? The problem is how, as I said, how the boundary components are displaced inside the unit sphere. So let's look only into that. Opa. Okay, so in this case here, the boundary components are like stuck in this way, right? And in this case, they are like this. Let me know if the pictures are not clear. Like, is this clear? More or less, like it's like two disks with some handles in the middle. Okay. Okay, so you cannot isotope this one into that one. Okay, so it's tempted to define the notion of boundary graph of a surface sigma in B3 as follows. So we associate a graph, which is really, you know, a discrete graph as follows. So I mean, it's harder to write it than to understand it. Then I will draw the picture. So sorry. So the vertices of the graph are correspond to connected components of the sphere minus the boundary components of sigma. Okay, so in this case we have 4 boundary components, one up here, okay, one in between these two boundary components, one in between these two, and one the last piece here. Okay, in this case, oh sorry, I already also drew the well, you can imagine what are the edges. And here we have also 4, one up here, one in the middle, one here, and one bounded by this circle here. And the 2 vertices are connected if there's a boundary component of sigma in common. And edges correspond to components of the boundary of sigma in this way. So, I mean, I already drew it. Here, there is this component of sigma that connects these 2 connected components of the sphere. So we attach an edge. Same thing here. Same thing here. And okay, here we have this big connected component that is adjacent to the other 3. Okay, is this clear? Okay. And we see that for sure, if the 2 graphs are different, then the 2 surfaces inside cannot be isotopic because the graph is preserved by isotopies. Okay, and so the theorem that we can prove is the following: is like okay, this is the only other the other topological information that we need. So, Choi Fraser. So basically okay, let me write it and then I say contribution. So every free boundary minimal surface, let me just write the acronym, sigma in B3 is unknotted meaning that it is isotopic to a model surface with the same genus that's still there, and isomorphic boundary graph. Okay. So, I mean, basically, you will see there's a step in the proof where we have to prove that sigma divides B3 into nice handle bodies. And this was already done by Choi Fraser, but they didn't really discuss the boundary graph, which is though more important for Self-Schringer. So that's how we kind of connected the two. Okay. Do you have questions about the statement? Okay, let me remark that here the free boundary condition, which means that the surface intersects orthogonally the boundary, is necessary. So the free boundary condition is necessary. Indeed, Hall in 1984, yes, constructed examples let's say examples of two minimal surfaces in the ball in B3 with the same genus and same boundary, not only, you know, isomorphic boundary graph, literally the same boundary, but not isotopic. So we really need the free boundary condition there. Yeah. That's a good question. Maybe with some angles. I'm not sure. So as we will see later, the validity of some monotonous is really related to the validity of a Frankel property. So I'm not sure that for some angles, there's some, or in some ambient manifolds with capillary, there's some Frankel property. In that case, one can opt for unknotedness. Yeah. It's a good question. Okay. And then, you know, this make, you know, like there's a natural question that arises that is, which boundary graphs can be realized? I mean, which graphs can be realized at boundary graphs of a free boundary minimal surface? Which graphs can be realized as boundary graphs of a free boundary minimal surface in B3? And this question is still open, so I didn't go into in this talk into, you know, the existence results for these objects that are many. In particular, let me just mention that recently, last year, Karpukin, Kuzner, McGrath, Stern. So in particular, this example there. So these four people constructed examples of free boundary minimal surface of every topology. So constructed examples of free boundary minimal surfaces with every topology, so genus and number of boundary components, but the boundary graphs of these examples are all stars, like this. So one example is this one, right? So their examples more or less look all like that. So the boundary graph is a star, okay? And so this question has been answered for every topology, but maybe it makes sense to say, okay, what about given another boundary graph? So this is open. There's just one case, so where we know that the boundary graph has to be special, which is genus 0. So for genus 0, so if sigma is genus 0, then the boundary graph is a star. Like this. And this is the result of Kushner-McGrath. So genus 0 examples are very special, but this is not true for every topology for sure, because we already have one example with higher topology where the boundary graph is different. Okay, so this was for free boundary minimal surfaces, but then let me go and talk about self-shrinkers. In R3. So again, let me write, we have a sigma, a surface in R3, which is minimal with respect to the Gaussian metric. So if you don't know minimal surfaces, self-shrinkers, you can just think of that. Otherwise, yeah, they arise as singularities of mean curvature flow. And again, the ends of the self-shrinkers of a self-shrinker is a complete minimal surface in R3. They can have different arrangements. Can have different arrangements. So what do I mean? Something similar to what we discussed before. So there could be a self-shrinker that, okay, does something in a compact set that we don't know, but then it has 3 ends, 2 going down, 1 up, 1 down, and 1 in the middle like this, okay? This is a potential self-shrinker. And then there could be another self-shrinker where the 3 ends are like this. Okay. So again, if we want to prove some sort of unknottedness, saying, okay, we have a model surface and we can, isotope this one to a model surface, this one to another surface, we have to take account this behavior because this one is not isotopic to the other one. Okay. Here, unfortunately, there are less existence results. So these 2 examples are not known, but is expected to, they are expected to exist, something like that. And let me remark that, okay, you can say why we didn't have the same problem for minimal surfaces in R3. It's because for minimal surfaces in R3, we are always in this case here, let's say. So let me write it. So this is different to than minimal surfaces in R3 because the ends of a minimal surface in R3 are kind of parallel, okay? Because ends of, because ends of minimal surfaces, let me rewrite it, in R3 are parallel in some sense, meaning that they are all graphs over the same plane, let's say. And so this says we cannot have some different configurations, okay? So that was why Mix-Yao result also, it's a bit different than our one. Okay, so Well, here they are not parallel, so we are tempted to do a similar definition to the boundary graphs for free boundary minimal surface, to do it here. So we can define, well, now it's not a boundary graph, but we can define a graph at infinity, let's say, of a self-shrinker. Well, in general, yeah, of a self-shrinker. Sigma in R3 as follows. We just take this definition in a ball sufficiently large. So we define the graph at infinity as the boundary graph of sigma in a ball BR0 for R sufficiently large. Okay, so why is this well defined? Well, the good news is that there's a structure theorem for the ends of a self-shrinker by Lu Wang. So this is well defined thanks to structure theorem by Lu Wang. About the ends of a self-shrinker. So the rough statement is that the ends of the self-shrinkers are asymptotic either to a cone or to a cylinder. Okay. So asymptotic either to cone or cylinder. And so you can see that, okay, after this large ball where they are asymptotic to cone or cylinder, it doesn't matter which ball I take, the boundary graph will always be the same. So again, here, the boundary graphs will be, you can take a big ball like this. There will be 1, 2, and 3 components. The boundary graph, the graph at infinity will be this one, same as there. And here, same thing, okay? 3 boundary components. The boundary graph, the graph at infinity is a star. Yeah. Okay. Okay, and now we can go back to this. Maybe I don't even need to erase all of it because we can state the theorem the same. So every self-shrinker sigma in R3 is unknotted. So it is isotopic to a model surface. We say genus, an isomorphic graph at infinity now. Okay. And actually, well, now it doesn't make sense, this remark anymore. Erase it. And actually, you can ask the same questions. Like, okay, now, well, we know much fewer examples of self-shrinkers in R3 with respect to free boundary minimal surface in R3. So for example, we don't know examples for every topology. So that's already a good question. But one can ask, which graphs can be realized as graphs at infinity? Of a self-shrinker in R3? So again, the only case where this question is answered is for genus 0. So for G equal to 0, we know that the self-shrinkers are the only possibilities are the plane, the sphere with a certain radius, and a cylinder by, again, work of Brandle. So for the plane, boundary graph is this. For the sphere, there's only one vertex. There's no ends. For the cylinder, it's like this. So differently from the case of free boundary minimal surfaces, maybe I raised it. Ah, no, it's there. So genus 0 free boundary minimal surface, you can realize every star. Here it's a bit more rigid. You cannot realize every star for genus 0. You can realize only 1, 2, and 3 vertices star. Okay. So we expect that, I mean, yeah, my expectation is that for free boundary minimal surface, you can realize every boundary graph. Every graph is boundary graph. Here, I'm not completely sure. Okay. Okay. So yeah, I have some time for giving a sketch of the proof. So feel free to ask questions if something is not clear. And well, I will sketch the proof of the self-shrinker case because it's a bit more complicated. It's also more new because the free boundary case was partially done by Choi Fraser. Maybe I take another chalk. Okay. 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 So we want to take a certain self-shrinker, and we want to prove that there exists an isotopy that brings it to a standardly like a model surface, or in some sense that this shrinker is standardly embedded inside R3. So looking back at this structure theorem by Lu Wang, we see that outside of a large ball, the self-shrinker behaves very well. So we don't really have to care about that. So outside of a ball of large radius, let me call sigma the self-shrinker that we are looking at. Okay, inside a large ball, sigma, the self-shrinker, is already, in some sense, unknotted, standardly embedded, whatever, okay? So it behaves very well. So if we can study, or like the thing is that if we can prove unknottedness inside the ball, we don't really have to care about it outside, thanks to Lu Wang structure theorem. Okay, so the problem is inside a ball of radius r. And here we need to use a topological result by Froman, let's say plus others. It's not exactly really just Froman, but the core is there, that says that it's sufficient to check that sigma is a strong, what is called strong eager splitting of this ball to prove that sigma is unknotted in the ball. Okay, so here we have our self-shrinker that does something here inside. And then it has ends, but we said outside everything is nice. So we look inside. And then, okay, it says, okay, if we have this topological property, then we have unknottedness. What does it mean, this topological property? It means that, okay, so the ball of radius r will be divided in two connected components by sigma, okay? C1 and C2. So here you have, well, one inside here, let's say, This is C1, and one outside, right? C2. Well, not quite, sorry. Actually, this is a bit more complicated case because it's like this. Here is C1 and here is C2 again, okay? It's connected, but it connects there. So maybe, let me draw a bit simpler. Let me do a one-dimension-less picture. So we have the ball of radius r, and then we have the self-shrinker inside, which is a two-dimensional surface. It's more complicated, but just to understand better. And then it divides in the ball. So outside we don't care. Inside we have C1 and C2. And what we, okay, that's always the case if we have a nice and nicely embedded surface. And what we ask is that basically sigma detects already all the fundamental group, the first fundamental group of C1 and C2. So there's a natural map from the first fundamental group of sigma to the first fundamental group of the two parts. And and we ask that this is surjective for I equal to 1 and 2. So basically saying, you know, at the level of the first fundamental group, already sigma detects all the topology that is in the two components. Okay, and so this is the meaning of strong Giger splitting. So thanks to Froman, we just have to check this one. So how do we do? Maybe let me take this picture here. So an equivalent, like a way to prove that is to take the universal cover. How did I call it? Oh, let me not call it. Or yeah, maybe capital P. I called it again P pi, but okay. Take the universal cover of let's say C1. Okay, so only in this component here we have some universal cover C1 tilde, and if the preimage of sigma, okay, so this one, so here there's sigma. This one is sigma. So if you see in the universal cover, this thing will have some boundary components. There will be some boundary components that are the preimage of sigma. Okay, so this is P, the -1 of sigma. And some boundary components will be the preimage of this part of boundary. So P -1 of the boundary of BR0 intersecting with C1. Okay? So if the preimage just of sigma is connected, then we have that property. So this is like a topology exercise. Okay, just by taking a curve here, see the lift, and you see that it implies that one. So our goal is to prove that if we take the universal cover, P1 of sigma is connected. And you see that, okay, the preimage of sigma will be some connected components. Okay, let's say sigma 1, sigma 2. And these ones are minimal surfaces. In C1 tilde with respect to which metric? So here they were minimal surfaces with respect to the Gaussian metric. So we have to take the pullback of the Gaussian metric. So did I give a name? Yes. Or in other, so of G1 tilde, which is the pullback, so P star of the Gaussian metric. Okay, and well, let me write it. Let me take this outside and write it as e to the minus gamma tilde. So this is just this term, but after the pullback, G tilde 0. Okay. So these are minimal surfaces in a certain space. We want to prove connectedness. This means proving a Frankel property. Okay, Frankel property means proving exactly that every two minimal surfaces have to intersect. You cannot have two disjoint. So, and here we see how, you know, this is not exactly the space that we started with. It's a universal cover. But we want to prove a Frankel property in the universal cover. So we expect that if the Frankel property holds in the base, then maybe it holds also on the universal cover. So how do we prove that? So there are many possible proofs that one can do of the Frankel property, but we use this kind of robust results by Keaton Naff and Jonathan Zhu, quite recent. Okay. So one thing that they prove is that any two self-shrinkers in a ball BR0 with R larger than 2 square root of 2 intersect. So exactly that, you know, a self-shrinker has to be connected. So they prove it at the level there, okay, of the base space. And well, let me mention that this result is improvement over results of Impera, Rigoli, Rimoldi, which prove the Frankel property, but in the whole space, and by Coldi-Minicozzi, which prove it in a ball like this, but without the quantitative estimate. Okay, so we go actually to their proof, because they have a sort of robust method to prove this kind of Frankel properties. So what they do, so again, what do we have? We have minimal surfaces in our case in that space. So, and we want to prove there's only one, okay? Minimal surfaces in C1 tilde with this metric. Maybe let me, yeah, that's right. With this metric, yeah, let me say G0 tilde, just the pullback of the Euclidean metric, but with respect to a weight. With respect to a weight, which is the pullback of the Gaussian weight. Okay, so here I said they are minimal surfaces with respect to this metric here. Well, it's the same of saying in respect of this metric G0 tilde, but with a weight. Okay, same thing. Why do I write like this? Because I want to add another weight, which is E to the F tilde. So if I add it in both places, nothing changes, okay? But I write in this way, and it will be clear in a second why, where F tilde, what is this? Well, this precise function is not so important. R square minus, so it's a logarithm of R square minus, okay, something like that. But the important part is that is a function that is infinity in this part. So F tilde is equal to infinity in this part of the boundary. So we have two boundaries, one that we don't like, we don't want to care about this one, okay? And the other one is that we care about, the sigma I. So we want to send the other one at infinity with a conformal change. So we do that. And so the boundary, let's say not at infinity, of this is just this sigma 1, sigma n, okay? And now the interesting thing is that, so here we can put this metric e to the f tilde g0 tilde. With respect to this metric, we have that the Ricci, I say tilde because in respect to this metric, but a weighted Ricci, so a -2 weighted Bakry-Emery Ricci, whatever, is not important precisely what it is, this is non-negative. So you know that in spaces with positive Ricci curvature, we have the Frenkel property. Two minimal surfaces have to intersect. Here we don't have positive Ricci curvature, but this other Bakry-Emery Ricci tensor is non-negative. And what Keaton, Nath, and Zhu, actually I wrote, I'm not sure there's a no or not. Well, yeah, okay. What they notice is that this is sufficient to prove Frenkel property. So they prove that then this kind of minimal surfaces, so n is equal to 1. So let's say Frenkel property holds. Okay, so that's sufficient. And well, this also kind of goes back to Marco's talk a little bit. So it's like this curvature assumptions, this weighted one. Well, you didn't talk much about the weighted setting, but you know, of weighting with a conformal factor to do what it's more convenient for you, etc. Okay, let me stop here. Thank you.
Thanks a lot, Giada, for this very clear talk. So, other questions?
So I was quite fascinated by the comparative discussion of the genus 1 case. So like the comparison between the case of shrinkers and the case of free boundary minimal surfaces, and in the genus 0 case. And maybe I didn't quite get it right, but I thought you mentioned some very optimistic conjecture about the realization problem in the free boundary case. So basically, my question was whether you really want to state it more explicitly. So in other words, in the genus 1 case or your favorite genus, what are the boundary graphs you expect to be realized in the for the free boundary problem?
The genus 0, we know they are only stars.
Yeah, but
so in this general case, so I don't know how they would change with the genus. I think we will get more and more graphs as the genus grows. But I think with all the genuses, we can realize all boundary graphs.
All trees, you mean?
Trees, yes, that's right. They have to be trees. Yeah.
Like even in the genus 1 case, you expect any tree to be the boundary tree of a free boundary minimal set?
No,
So,
not in the genus, sorry?
Say, for instance, in the genus 1.
Well, no, in the genus 1, I'm not sure. No.
So there are...
there are more and more as the genus goes on, the genus grows. So for genus 0, they're only stars. I don't know what for genus 1, but maybe stars and...
But then you are saying there will be restrictions, in fact.
There will be. Yeah. I just say probably for every tree can be realized, but not...
okay, yeah. For some genus. Yeah.
That's right.
Okay. No, that one is plausible. Yeah. Okay, thank you.
Thank you for very nice talk. At some point you mentioned that there are counterexamples in the hyperbolic space.
Yeah.
Do you expect counterexample also in the case of self-expanders instead of self-shrinkers?
I don't know about that. Yeah. Yeah, someone asked me already about expanders. Do you know if there's some sort of Frankel property for expanders?
I don't know.
It's no. Yeah. So I think that would be the first thing to understand, if there's the Frankel property. Yeah.
Yeah, just a curiosity about those counterexamples in the hyperbolic space. Are those surfaces embedded? Do you know?
I think yes. Yeah. They should be abandoned. I have to say I didn't read the paper, so I'm not 100% sure. I just talked with Mark, sorry. But they should be abandoned, yes.
Okay, thanks.
It sounds strange to you or no?
No.
Okay. Yeah.
Okay, if there are no other questions, we can thank the speaker again.
Yeah.
Okay, so we proceed with our next speaker, who is Semyon Dyatlov from MIT, who will talk about control of eigenfunctions on negatively curved manifolds.
Thank you. Well, first I'd like to thank the organizers for inviting me. It's nice to be able to speak in Pisa again. And I should say that this talk is going to be, the topic of that is going to be quite different for most of you. So I will try to give more background, and maybe I'll be less of the technical details of the proofs. I'll keep some of the things as hand waving as opposed to precise statements. So if you press me, precise statements can be given. Well, the theorem I will state, the first theorem I will state precisely. And so at least I can state a result. So this is various parts of that are joined with Jed Athria, Jean Bourgain, Long Jin, Nick Miller, and Stefan Nonnenmacher. So here's a theorem that's due to myself, Jin and Nonnenmacher, and this was in 22, and this uses my older result with Bourgain in 2018. So here's the result. So this one is going to be for surfaces, and that's an older result. And then I'm going to talk about what's known in higher dimensions. And then I will try to give some picture on how this works inside. So the setting here is going to be for surfaces, you will take a negatively curved surface. More precisely, it should be compact, connected without boundary. Okay, so you have a negatively curved Riemannian surface. Everything is going to be smooth in this talk. And then I'm going to fix an open set, omega, inside of my surface. And it's going to be non-empty. Maybe I'll draw the surface here. I'll do it like that. Here's my surface. Here's omega. Then, what's the conclusion? Well, the theorem is about Laplace eigenfunctions. I forgot to say that. And I'll provide more context and motivation as I go along. But okay, let's start with a statement. So the theorem is about Laplace eigenfunctions. And it's a lower bound. So it says that if you have a Laplace eigenvalue, which for reasons to maybe become clear later, I'll call the eigenvalue lambda square. If you have an eigenfunction of the Laplace-Beltrami operator, then the L2 norm of that on omega is bounded below in terms of the L2 norm on the whole surface. And what are the quantifiers here? Well, you have some positive constant that quantifies this upper bound, a lower bound, and it is not dependent on the eigenvalue. Okay. So it's a lower bound on mass on an eigenfunction. You take a Laplace eigenfunction, negatively curved surface, you fix here in an empty open set, then I can give you a lower bound on the L2 mass in that set. Okay. A boundaryless surface. No, the eigenfunction is on M. Right. So, if you do control theory, you should think of omega as some kind of control set. You can think of omega as a small ball. There's nothing taken away from the theorem. It's just taking omega to be a small ball, because the theorem is obviously monotone. If you prove it for a smaller set, you prove it for a bigger set also, so you can replace it with a small ball if you want. Okay, so yeah, so it's just a statement about Laplace eigenfunctions. That's a fairly elementary statement. But it turns out that, well, the proof that I know is not quite elementary, and also the negative curvature assumption is needed in an essential way. So I will have to, I have a few goals to hit in this talk. I'm not sure how many of them I will actually achieve, but one of the goals is to explain where negative curvature enters. Another goal to explain what fractal sets have to do with this. I haven't said anything about fractal sets yet, but they will be important. But at least I can give you this example. Maybe everybody's favorite manifold, compact surface is a S2 with a round metric. If I take my control set somewhere in, say, the southern hemisphere, then you can find eigenfunctions which will be exponentially small in terms of the eigenvalue on omega relative to everything else. On a sphere, we know what eigenfunctions are. They're spherical harmonics, and in particular, they are the Gaussian beam spherical harmonics. And those they're really concentrated on a small neighborhood of the equator. So the L2 mass everywhere else, it's not zero, but it goes exponentially small as the eigenvalue goes to infinity. So I should stress that the key property of this theorem is that the lower bound does not depend on the eigenvalue. If you allow the lower bound to depend on eigenvalue, that's just unique continuation, right? If you freeze lambda, that's just an elliptic unique continuation. There's nothing else to it. And so the interesting part of the theorem is that in this setting, this lower bound on mass does not degenerate as the eigenvalue goes to infinity. Okay, so it's really a high frequency eigenfunction statement. All right. Okay. Yeah, so with a bit of history, in the hyperbolic case, this was proved by myself and Jin. And that was a few years before myself, Jin, and Onmash. And then variable curvature offers additional challenges. And so that was done in this paper. But no, before our work, it was not known. The only manifold for which it was known, well, okay, there's a circle, and then the flat tori. And that's true there, but for a different reason. So I'm not going to go into that. Okay, so let's see, what do I want to say? Well, there are some applications. Maybe I'll skip applications for today. So let's just think of it as a spectral geometric statement. And now another thing that provides challenges, in addition to going from constant to variable curvature, is going to higher dimensions. And so as you can see, this theorem is not very new. In fact, the paper was finished 6 years ago. And since then, part of our work has been to understand what can you say in higher dimensions. So this proves to be complicated for several reasons, but one of them I'll explain. So now I'm going to do a complete 180 pivot, and I'm going to talk about the main tool used in the proof of this theorem. And then at the end of the talk, I'll have to tie those together. So unfortunately, it's going to run as 2 parallel talks for some time, and then hopefully it'll coalesce. But in explaining the main tool, I will also explain where one of the problems in higher dimensions lies and how it can be overcome. And so the main tool is known as a fractal uncertainty principle. It was developed for this kind of problems specifically. Well, first let me say about the usual uncertainty principle, and I will mostly draw pictures, even though I could state the statement, but I'm not sure is the right thing to do here. So imagine you have a function in L2 of R, and imagine that you know that the Fourier support of f lies, let's say, in a unit interval. Okay. Now, what's the uncertainty principle in quantum mechanics? A particle cannot be too localized in both position and frequency, right? How do you translate it into mathematics? The localization in frequency is understood in terms of the Fourier transform. So uncertainty principles in harmonic analysis, they all have the following form. if the Fourier transform, if a Fourier transform of a function is concentrated in certain ways, then the function itself cannot be concentrated in some ways. And the most basic example is this. If you take a function whose Fourier transform is supported in a unit-sized interval, well, I'm going to draw the graph of that function. It's a nice smooth function. Right? Now, if I take the norm of f in L2 of a small interval, so here h will go to 0, then this norm will be small. Your function cannot be localized in a small interval because of this Fourier localization statement. There's a million ways to prove that. Use Sobolev embedding if you must. No, but if it's band-limited function, if I take an interval of size h, the L2 mass on this interval will be no more than h1 half times some fixed constant times the L2 norm everywhere. Okay. Right. Of course, what I could also do is instead of having a function which is supported in a unit interval centered at 0, I could shift my interval. And then my function here, instead of looking very nice and smooth, it might have a lot of oscillation. But really, it's just e to the I eta 0x times the slowly varying function. So this property is not going to change. So if I have a function where the Fourier transform is localized in any unit-sized interval, then its mass on any small interval in position has to be small, right? My h goes to 0. Now, a fractal uncertainty principle tells me, and that's where I'm going to be vague, is that if the support of a Fourier transform of a function is inside some fractal union, that's where I try to avoid to define exactly what I mean by fractal union of, let's say, unit intervals, then the norm of f restricted to L2, restricted to an h neighborhood of some other fractal set will decay like some positive power of h. Okay. Here our sets were just points. You had a function with Fourier transform in a single interval. You restrict to a single h-sized interval the function itself. You get h to 1/2, so you get beta equals 1/2. Here you have some kind of notion of what it means to be fractal. I will say a more precise way to say it is porous. That's the kind of thing I require. I need my set to have a lot of holes at different scales, at different levels, different places. So if you have a function where you know that the Fourier support is inside some porous union of unit intervals, then the mass of this function on h neighborhood of another porous set is going to be small. Okay? All right, so that's this impressionistic way to state the fractal uncertainty principle. Oh yes, definitely. Sometimes I tacitly normalize everything to be 1 in L2, but you're absolutely right. Yes, relative to what? Small relative to L2. Okay. Now, maybe I'll erase this uncertainty principle. And I should say, if you're trying to think what do the LP norms do for this, if you use the fact that Fourier transform is bounded L1 to L infinity, you can get this result for fractal sets of dimensions strictly less than 1/2. It's a very nice exercise. But the point of this result is that it actually works for any dimension strictly less than 1, which is considerably harder. Now, it turns out that when you do theorems like that for surfaces, you need to use fractal uncertainty principle for functions on the real line. That'll become apparent later. One dimension is always removed somehow in the argument. So if you want to prove something like that for higher dimensional manifolds, you want fractal uncertainty principle in higher dimensions. So you want to say something like, if I had a function L2 of Rd, its Fourier transform is supported in some union of size 1 poles, then you restrict it to some other fractal set, it's small. And that would be great. The only problem with that is it's false. Okay? So in higher dimensions, so higher dimensional FUP, as stated naively, fractal uncertainty principle fails. And here's a picture. So that's where drawing pictures is maybe better than writing exact formulas. So I'm going to take my favorite function in L2, which is, let's say I'm in R2. I'm going to take delta function of x2. Okay, it's not in L2, but that's sort of not relevant to the counterexample. So I'm just going to take a delta function on a line. Now we can argue whether a line is a fractal set or not. Okay, but in my definition it is. At least in the most naive generalization of that it is. I didn't define what porosity was, but if you take any ball of some radius, you can find a ball of half the radius that doesn't intersect the line. And that tells me that the line is porous on balls. But of course, okay, let's say this was f hat. So what is my f then? What's the Fourier transform of that? Well, it's going to be some prefactor, depending on how you define the Fourier transform, delta of x1. Right? The Fourier transform will be lying on a vertical line. Which, of course, again, is porous. So here's an example of a function supported on a fractal set whose Fourier transform is also supported on a fractal set. So a naive generalization of this fractal uncertainty principle would fail. And that certainly uncomfortable. So now I'm going to erase this statement, especially since it's not true. Yet, you can actually do something with that. So now, this is to explain one of the difficulties in higher dimensions and maybe justify why the results in higher dimensions that I will state have a much more partial and much less definitive character than the result for surfaces. See, for surface, it was any negatively curved surface, could be variable curvature, any non-empty open set. Here, the results tend to be longer to state. So here's the first result. Opa, where is it? So here's a work of myself, Athreya, and Miller. Wow, I just realized it spells like ADM mass, but okay. Yes, 24. And here's the setting. So the setting would be MG is compact, complex hyperbolic quotient. So compact quotient of CHN. Okay? Take complex hyperbolic space, take a compact quotient. It's not so easy to construct those, but people know they exist. It's much harder to construct those than usual hyperbolic manifolds or hyperbolic surfaces. And then I'm going to assume that my control set omega intersects every submanifold of the following kind. I assume it intersects every compact, immersed, totally geodesic, complex submanifold. Okay, there you go. So previously we had any non-empty open set. Here the theorem is decidedly weaker. I should say I conjecture that this theorem is true. Of course, you can conjecture anything, but there are no counterexamples known to me to this theorem being true just for any negatively curved manifold. And negatively curved would be negative sectional curvature, any dimension, you know. But we're quite far from that. But what we can show is that if you take a complex hyperbolic manifold, then it works as long as your open set intersects every compact immersed totally geodesic complex submanifold. Okay. Sometimes there are plenty of those, well, at most countably many. Sometimes there are none, no. But that's what we can say. So yeah, theorem 1 holds, I should say. So the same kind of statement holds. And there is a newer result, right? I should say this one still uses one-dimensional fractal uncertainty principle. I don't think I'll reach this part at the end of the talk, so I'll squeeze it into the beginning. The reason why is that complex hyperbolic quotients, they have a certain dedicated direction. And when you do the stable and unstable decomposition, there is a single fast, one-dimensional fast space in which if you perturb your geodesic, it will diverge from the original twice as fast as in any other unstable direction. And because it's one-dimensional, we are able to still use this. And that's why we started with complex hyperbolic manifolds. Now, there's a more recent work with, well, not with, by Elena Kim at MIT and Miller. That's, I believe, 25. Is it 25? Maybe still 24. No, 25. So here is this setting. You have, in a way, the first setting that you would consider in higher dimensions, which is a real hyperbolic quotient. And then omega intersect n for every n compact immersed totally geodesic submanifold. Okay, in the complex case, the abstractions are given by complex submanifolds. Here, well, there is no complex structure at all. So here it's any submanifold. Well, of course, of dimension at least 2. I should say the theorem is very easy to prove if your omega intersects every geodesic. Okay. So if your control set intersects every geodesic, this is well known. It's called the geometric control condition. But here our abstractions, they start in dimension 2. So for example, you can say, well, I have a hyperbolic 3 manifold. I need to intersect every compact immersed totally geodesic surface. All right. So these would be my abstractions. And what this does is this uses recent work by Cohen in, I guess, 24, 23, depending on the publication date. Publication date, I guess, would be 25. And this one works already. Yeah, it's a little bit confusing to tell this story, because when we started, we only had one-dimensional result. And so we did what we could with the one-dimensional result. Later, Alex Cohen, also still at MIT, I guess, for another few days, as a graduate student, managed to actually prove this fractal uncertainty principle in higher dimensions. Of course, you have to adjust the statement because, as I just said, it's false. But what he showed is that he requires one of the sets be porous on lines. I'm not going to draw this condition, but in particular, containing lines is prohibited. And it turns out that this is something that we can actually verify for the sets that we have. And this is what Kim and Miller did. Okay, so that's the statement of results. It's, I know, admittedly, it's a bit of a handful. The story was simpler 5 years ago when we were restricted to surfaces. Now, if there are any questions on the results, I'm happy to address them. And yes? Yes. So, right, so what Cohen showed, so higher dimension of EP fails. Well, he showed that it holds, but you need porosity on lines. So let me just put it in writing. And the condition is the following. I have another color here. Beautiful. So instead of the porosity on balls was in each ball, you can find a sub-ball of some fixed relative size that doesn't intersect your set. Porosity on lines is on every line, on every line segment, you'll be able to find a point. Let's say this is length alpha, so that the ball of radius nu times alpha, where nu is positive, the porosity constant, does not intersect your set that you want to be porous. And so a line is porous on balls. Any ball, you can find a half ball that doesn't intersect the line. But a line is not porous on lines, because you can take any segment on the line itself, and then you won't be able to find the ball centered on that segment. So it's a stronger condition. But luckily, it's a condition that's natural enough that you can still reformulate it using the machinery of this proof in a way that can be verified, and you can quantify what abstractions you get. I should say again, we don't know if those abstractions actually ever appear. Conjecture is that it's true without any additional assumptions, but that's what we can prove. All right. So I don't see any other questions. So what I'm going to do is I'm going to now... So it was this part of the story with fractal sets and higher dimensions. Now I'm going to go back to this talk, and I will tell you about a more advanced version of this theorem. When I have a friend who does... you could say geometric analysis, but I guess more elliptic PD. And when I first told him about this result, he said, where do you use negative curvature? So you multiply somewhere, then maybe you integrate by parts, and then the curvature tensor comes out. So this is not one of those results. And I mean, I challenge, if anybody can prove it by integration by parts, and the curvature tensor just comes out somewhere in for hyperbolic surface, it would be really cool. I'd be very happy to see a proof like that. But the proof we have is much more indirect, and it uses a lot of the dynamics of the geodesic flow that I'll get in a moment. And also inside the proof, it proves a stronger result in localization and position and frequency. Now, this result is harder to state, which is why I don't start with it. But this reformulation is essential to understanding how to actually prove this. So I have to spend some time talking about localization in position and frequency, which is also sometimes called microlocalization. Okay. So here's a 5, at most 10-minute lecture on microlocal analysis that nobody asked for. So what we're going to do is, previously we had a manifold and we had an open set, and we're localizing our eigenfunction to this open set. You can restrict it literally to the set, or you can think of it as multiplying by a cutoff function that's supported inside of an open set. In my business, it's often good to have things that don't have boundary. Instead, think about the cutoff functions so that you don't have to deal with any singularities that would come from the boundary. Now, microlocalization would allow you not only to localize your function in a certain position, but simultaneously to localize it in a certain frequency. And so if you have information, microlocalization of a function, it gives you more information than just localization in position. I'll give some examples, but first I'll give a sort of a definition. So here I will have my M will be some manifold, and I'll have letters X for the position variable and Xi for the momentum variable. Now I should say that below is really motivated by quantum mechanics. In fact, the basic form of that construction, the wild quantization, does come from quantum mechanics. And I'll try to explain the physical relevance of the result once I'm done with my microlocal lecture. So now let's say I have a function A of position and momentum. Well, what is momentum geometrical? It turns out it has to be a cotangent vector. There's several ways to make sense of this, but I said that we'll talk about localization and frequency, and localization and frequency is localization in the Fourier space. Now, when you define the Fourier transform, you take the inner product, right? Most sane people do that, except harmonic analysts sometimes, right? And what a harmonic analyst would do, well, the most basic version is you would start with a finite dimensional real vector space, and then your momentum space would be the dual space, right? Because then you can multiply a vector and the covector without fixing the inner product. And so it stands to reason that the momentum variable should actually be a cotangent vector, okay? And so your algebra of classical observables, there will be functions on the cotangent bundle, okay? So if you start with a function like that, and sometimes I'll assume it's compactly supported, and sometimes I won't, depending on my own convenience, I can define its quantization which is it's going to be a family of operators on L2 of M. This is quantum mechanics. If you start with a classical observable, which is a function of position momentum, you convert it to a quantum observable, which is an operator on a Hilbert space. Here, my position momentum space, the phase space, is a cotangent bundle. The Hilbert space is just the L2 space of the corresponding manifold. And informally, you can think of it as taking this function A of multiplication operators by X and minus IH times the differentiation operator, okay? Algebraically, it makes no sense, at least at first, because differentiation, multiplication don't commute. What really happens is that in the asymptotic limit, as this parameter h goes to 0, the leading part of this can be recovered canonically. So there's many quantizations, but they all produce the same result up to error terms. And my h here is going to be lambda inverse, so 1 over square root of the eigenvalue. That's going to be the significance of that parameter. Now, if you think, of course, physically h is the Planck constant, but Planck constant is not actually dimensionless. So it doesn't make sense to let Planck constant go to 0, right? It's nonsensical. What you do is you let the effective h go to 0, and this effective h, it's the wavelength at which your eigenfunction oscillates. I'll give 2 examples of eigenfunctions on the torus, and then we'll see it. Okay, so it turns out that we can start with a function and quantize it. I'm not going to give a definition of that. Instead, I'm going to give 2 examples. If a is a function of x only, then a quantization is very simple. It's a multiplication operator. Okay, so no surprises there. Now, the xi variable is more mysterious, but if my manifold was Rn, and I had a function only of the momentum variables, then the usual quantization will give you a Fourier multiplier. And so it will do this. Up h of a hat u of eta is a of h times eta u hat of eta. Okay. It will be a multiplier on the Fourier variable. And you can see that your frequency is eta, and it's going to be xi over h. So the way the asymptotic parameters work is my momentum will be fixed. It will actually be unit length. The h, which is 1 over square root of eigenvalue, will go to 0. And then as the eigenvalue goes to infinity, the frequency at which we're studying is going to infinity. Because eigenfunctions oscillate more and more. And that captures the correct scaling for that. So you see that if you have a function of only one of these groups of variables, you just get a multiplication operator. And then you'll just have to trust me, you can somehow combine the two to get sort of a multiplication in position frequency space. Now, once you know how to multiply your functions in position frequency space, you can talk about localization position frequency space. I can take a of x and xi that is supported in some compact set in both x and xi variables. It doesn't have to be a product. It can be something complicated. And then I can apply to my u, and I say this micro-localizes my u in position frequency. Right? So it's an algebra that combines position cutoffs and frequency cutoffs, and a lot more. Okay, so we have that. Now let me give you an example. Okay, so unfortunately, I could show numerics, but there's no formulas for Laplace eigenfunctions on hyperbolic surfaces. They're notoriously difficult to study using any kind of explicit methods. But there is one manifold which is not negatively curved, but on which eigenfunctions are very easy to write down. At least some eigenfunctions are very easy to write down. And it's the 2 torus. It's a kind of the first non-trivial example. So the theorem, well, that doesn't apply to that, but the concept of microlization does. So what do you have here? Let's say it's r squared by 2 pi z squared. This is my torus. And I can look at the following eigenfunction. U of x, 1x2, is e to the I k x1. Right? My eigenvalue is going to be k squared. H here is 1 over k. That's my wavelength at which it oscillates. And if you plot this function, well, if you only study the localization of the L2 mass in position, you will only study absolute value u squared as a function. And this is just 1. So if you look at this function, you just look from a point of view of its position localization, it's equidistributed. It's distributed equally everywhere. Right? But not so if I look at it in frequency. Right? If I actually plot the function without taking absolute value square, the level sets look like something like that, right? And this distance is, I believe, 2 pi h. H being the wavelength. And so your eigenfunction, it looks like this, right? It oscillates in this direction. And you can see that this function is actually micro-localized to any position. There's no useful position localization you can get out of this. And the frequency, or the momentum, will be the vector 1, 0. Sort of on the picture, that's why we call one version of localization the wavefront set, is because your frequency localization vector will be perpendicular to these fronts. For a simple looking function like that, okay, most eigenfunctions are going to look like a mess, and but for a very simple looking function like that, you see the oscillation is only in this direction. It makes sense. If you take the Fourier series of that, it only has one coefficient, and it's at h inverse comma 0. Right? Or if you want, if I applied a nice smooth cutoff to this function, and then I took the Fourier transform, okay, it's not going to be supported at single point, but it'll be supported in a small cone around only these directions. Of course, you have another function here, I should say. I can do the same with x1 replaced by x2, and then you will get xi1 equals 0, xi2 equals 1. So this torus eigenfunction will look like that. Pardon my bad drawing. Right? So you have two functions. Localization and position is the same. Absolute value square is 1 for both. But one of them only localizes in frequencies going this way, and the other one only localizes in frequencies going that way. Okay? So that's a good example of how micro-localization is more than just localization. A nice exercise, you can check that both of those sets are invariant under the geodesic flow. Right? In fact, they are the Liouville tori of Liouville tori of the associated completely integrable system, the geodesic flow on the torus. In negatively curved manifolds, however, there's no complete integrability of the geodesic flow, and so something else happens entirely. And what happens is you get delocalization, you get lower bounds in both position and frequency. So here is a more advanced version of the theorem, which, yes, a little bit more painful to state, but if you have M, G, compact, negatively curved, let's say, surface, and you assume that you have an observable which satisfies a few assumptions. Well, it's smooth, it's not negative, and it's not identically 0 restricted to the cosphere bundle, which turns out to be the correct assumptions. Then the following expression has a lower bound as h goes to 0 for Laplace eigenfunctions with eigenvalue h to the minus 2. So it's again a lower bound. Previously, we had a lower bound on the L2 mass in S set. Here, this one I claim is a stronger one. It's a lower bound on the localization of your A in position and frequency to any sets of positions and frequencies which intersects the cosphere bundle. It turns out it's not too hard to show that if you try to localize your eigenfunction to frequencies away from length 1, so momentum away from length 1, you just get something very small. Note here, both of those, 1, 0 and 0, 1, were unit vectors. It just has to do with the normalization of h being 1 over square root of the eigenvalue. But if you localize it anywhere that includes at least one point in the cosphere bundle, then you have a lower bound. Now, from a quantum mechanical point of view, this actually has a natural interpretation. So this is where I'll give you a lecture on quantum mechanics by somebody who never actually studied quantum mechanics formally, that you definitely didn't ask for, but it'll only take a minute. So in quantum mechanics, imagine that you live on a compact negatively curved surface. Personally, I would not recommend living on one. But imagine you somehow manage to get a particle that lives on one. Then the Laplace eigenfunctions would be the pure quantum states of the corresponding particle. That's the quantum mechanical interpretation. Everything is usually it's nice to think about everything as being decomposed into pure quantum states. And what is this expression? In the usual interpretation of quantum mechanics, the Copenhagen interpretation, this is the average value of the classical observable on the corresponding wave function. So you take a function of position and momentum, and this expression tells you the average value of the of that function on this quantum state. Right? You see, the special case is if A was a function only of position, this is a multiplication operator. Right? Maybe I should say this somewhere. If A is A of x, then this expression, which, by the way, if you, unlike me, did take quantum mechanics, the physicist would denote it this way, if this helps. It's just this, is absolute value u squared times A integrated. So that's the quantity we were estimating before. And so if you apply this theorem to only functions of position, you recover the previous theorem, which is much easier to state, but is weaker. But here you can also localize in frequency. So for example, those toric eigenfunctions, they do not satisfy this lower bound, right? They're equidistributed in position, but not in frequency. On hyperbolic surfaces, we can show that, well, we can't show equidistribution, but we can show lower bounds in both position and frequency. All right, so now, so I should go until 30 past, is that the idea? Okay. All right, so I have a bit less than 20 minutes. So I'll try to spend half of this time giving more background for how people study those high frequency limits of eigenfunctions and tying this result together with previous things, because the subject has a long history and it will certainly be not proper to omit it. And then I'll try to, in a few words and pictures, explain how the proof has fractal sets appear and where, you know, the fractal uncertainty principle ties into all of this. And for that, I'll just stick to dimension 2. So, but first, here is a bit of history. Yes. Yes. Oh, definitely. If A is bounded below by 1 on the cosphere bundle, you can just take the constant to be 1. What you can show, if A is identically 1, this is the identity operator, you just get 1. If A is localized away from the cosphere bundle, or if it just vanishes on the cosphere bundle, you can show this expression is very small for eigenfunctions. So only the values of A on the cosphere bundle matter. You can see more actually using this technology that I'll explain in a moment. If A if A integrates to something positive on every geodesic, and here every closed geodesic is enough because it's negative curvature, then this is also easy to show. But we can do it for A, which is in a small ball, which in particular avoids a lot of closed geodesic that exists on those surfaces. The trivial part does not need any curvature assumption. That's correct. So now I'm going to say something that some of you might find appealing, even though my objects here are more linear. Not quite, they're quadratic. You know, when you have this kind of bounds and you have eigenfunctions, and you have something go to infinity. Here my h goes to 0, the eigenvalue goes to infinity. It's natural to try to look at the limit, prove some kind of compactness, and classify all possible limits. It is, of course, a very different context than the way it is applied in geometric analysis. But this idea is appealing here too. And it turns out that those limits exist, and they are given by measures with some nice properties. And so I'll explain what these measures are. And in this context, I can explain a bit of the history of the question. So to get a limit, you need a sequence. So I'm going to take some sequence of eigenvalues. So, sorry, what did I do? My eigenvalue will go to infinity. My eigenfunction will be L2 normalized, no harm in that. Like that. So I take a sequence of high energy eigenfunctions. Eigenvalue goes to infinity. And my semi-classical parameter aj will be lambda g inverse. I will say that my uj, really sort of uj square in some sense, converges to mu, a measure on T star M, if. So this concept is a generalization of a weak limit of probability measures. How do you define a weak limit of probability measures? You take an arbitrary observable, then you take the expected value of that observable with respect to your measure in the sequence, take the limit, you should get the expected value with respect to the limiting measure, right? From this point of view, it's a perfect extension of that, except we're going to use those expressions. So with that in mind, I say for every observable, here it's convenient for me to have it compactly supported in T star M. If I take this expression, which is sort of the average value in the quantum world, the inner product is in L2, of course, I forgot to say, converges to the integral of A with respect to this measure. Okay. Right. So that's my notion of weak limit of these probability measures. Yeah. So what do I want to say about those measures? So this is it's a macroscopic it gives you a macroscopic feature of your eigenfunction. It doesn't forget about oscillations. It puts them into frequency localization. But for example, you cannot extract something like, for example, the nodal set, so the set where it's 0 from this description and so on, because you first fix your observable, and then you let the eigenvalue go to infinity, right? So that's why it's macroscopic. You can show that for the two examples that I erased, I think they were on this board, on the torus, e to the ikx1 will converge to a delta measure of x1 to the volume measure on the base, tensored with a delta measure on just one direction. So it'll be localized to a natural measure on a Liouville torus of that, of this integrable system. But what do we know in general? Well, so we know some properties. The first few are fairly basic once you study the properties of this quantization. Well, these measures exist. There is a compactness statement. The support of each of these measures turns out to be in the cosphere bundle, and their probability measures owing to the L2 normalization. See, now I fix L2 normalization. I'm not going to be caught on not putting the L2 norm again. Less intuitive property is that mu is invariant. So each of these measures is invariant under the geodesic flow phi t, which is a flow on the cosphere bundle. No, I know in Riemannian geometry, you like to think of geodesics as they lie on the base. But when you think of geodesic flow as a dynamical system, you should really think of it as a flow on here, for example, the cosphere or cosphere bundle. Doesn't matter. For me, it's more convenient, the cosphere bundle. So when you have a starting position and a starting velocity, then you trace it for some time, you get the new starting position, new starting velocity. And it turns out that all of your measures are going to be invariant under this flow. So that's how you could show that if you have A, which integrates to something positive on each geodesic, a simple, real analysis argument will show that each corresponding limiting measure, well, its support has to intersect every geodesic, and thus it's because it's invariant in the geodesic flow, it has to be supported everywhere. So here are some much less obvious, much less direct to derive properties of this. So one is called quantum ergodicity, and that's really the result that maybe started that branch of quantum chaos to which my talk belongs. That's due to Schnirelmann in the 70s, at least the statement, and then Zeldich and Colenti-Verdier in the 80s. So quantum ergodicity says that if phi t is ergodic, then most eigenfunctions converge to the Liouville measure. Okay, a few to unpack. There is a natural invariant measure under the flow on the cosphere bundle, the Liouville measure. It's the most natural measure. It's d volume times the ds in the sphere variables, normalized to be a probability measure. That one is invariant. And then what quantum ergodicity tells you is that if your geodesic flow is ergodic with respect to this measure, for example, this happens on negatively curved manifolds, but there are more examples when it happens. then you have a density 1 sequence of the whole Hilbert basis of eigenfunctions, which converge to the Liouville measure. So this means they equidistribute. And this is a very strong property because it means that in the limit, the probability of finding your quantum particle in some set in position frequency space becomes proportional to the volume of that set. Now, there is, I'll do this. There is a conjecture stated originally by Rudnik and Sarnak in 1994 called quantum unique ergodicity, is that all eigenfunctions converge to the Liouville measure. So not just the density 1 set. And that one's still very open. But what we showed in this theorem, I know, this sort of, okay, I know what I can do. I can flip those boards, and then you can see here, this theorem, what does it tell you about the limiting measures? It tells you that their support is equal to the whole cosphere bundle, which is much less information than being equal to the volume measure, but it tells you that they charge every ball, every non-empty open set. That's from here, from whichever theorem, from this theorem, you can pass to the limit to get this. And I should say there is also a result known as entropy bounds due to Anantaram and Nonnemascher, which gives you another kind of flavor of lack of localization for those limiting measures, but it's stated in terms of entropy as opposed to support, and sort of orthogonal to this theorem. Okay, so that's my context for the for the theorem. So if you want to view it in kind of historical context, people studied quite a bit those semi-classical measures because they're nice limiting objects that encode macroscopic concentration in position and frequency space of high energy sequences of eigenfunctions. And what this theorem tells you is that on negatively curved surfaces, each such object will have full support. And then the higher dimensional versions, they are also formulated in the sense that each such object has one of those obstructions. It will have the cosphere bundle of one of those compact immersed blah submanifolds. At least that's what we can prove. Okay, great. I have less than 1 page left and about 5 minutes. Are there any questions about the historical context? It's a compactness statement. Yeah. That's right. That's right. Well, that's how compactness, there's always a subsequence, right? Well, if, right, the quantum unique ergodicity conjecture is under negative curvature. You see, what I did here is that I only considered negatively curved manifolds, but if you look at quantum chaos, people studied a lot of things. So, for example, if you take the round sphere, any invariant measure can be a semi-classical limiting measure. And the way you would do it is any invariant measure can be approximated by some linear combination of delta measures on closed geodesics. And then we have those Gaussian beams, or Gaussian beam spherical harmonics, and they concentrate exactly on those closed geodesics, and you can cook up the correct linear combination to get to any measure you want. But the idea here in quantum chaos is that if the geodesic flow has some kind of chaotic behavior, then your eigenfunctions have to spread out in some sense. And quantum unique ergodicity is a version of that. So the conjecture is that if you have negative curvature, which makes it for a strongly chaotic behavior of the geodesic flow, then all of your eigenfunctions equidistribute. Quantum ergodicity has well, it's first of all, it's better than quantum unique ergodicity because it's actually known. It's a theorem, not a conjecture. It has a weaker assumption. You only need ergodicity of the geodesic flow, which is weaker than negative curvature. It's still a chaotic assumption. But it also has a weaker conclusion because it only tells you that most eigenfunctions equidistribute. Yeah. You can see, there's a bit of a zoo results, but this result is one that does belong in that context. So now, let's see, what can I tell you? Well, I can tell you a little bit about how the proof works. At least I can say where the fractal sets come by. Okay. So proof in quotes, not because the proof is not complete, but because my exposition of it will be very short. So what you will do is, first of all, I'm going to assume that I have the setting of hyperbolic surfaces. So my curvature will be exactly -1 for the purpose of this exposition. And then where does the negative curvature come in? It comes in the stable unstable decomposition of the geodesic flow. That's a rather strong chaotic property of this geodesic flow and gives you kind of exponential divergence from the original trajectory. So in differential geometric terms, you can write the sphere bundle, or the tangent space of the sphere bundle of this, or the tangent bundle of the cosphere bundle, really, splits into 3 directions. So the cosphere bundle here is 3-dimensional, right? We're surface, cosphere bundle is 3-dimensional. And you can write it as direct sum of 3 sub-bundles. Here they're actually smooth, which makes it nice. And one of them is the flow direction. The other one is the unstable direction. And the other one is a stable direction. And the property is that the flow direction just contains the generator of the flow. So if you perturb your geodesic in the flow direction, it just shifts. Okay? Again, maybe a Riemannian geometer would think of it in terms of certain spaces of Jacobi fields, but it's equivalent. Now, if I take my differential somewhere and I apply it to an unstable vector, I'm going to get this unstable vector multiplied by e to the t. Okay, it's not in the same tangent space, but for example, it expands by e to the t with respect to the Sasaki metric. Or there is a canonical vector field here. So what happens is, if you take your initial geodesic and you perturb in the unstable direction, sometimes it's also called a horocyclical unstable flow, then as you go forward, your geodesics will diverge exactly exponentially fast in forward time, and they will converge to each other in the backward time. And for the stable vector, you will get e to the minus t. Right? So you have this kind of stable unstable splitting. Now, remember from the theorem that we were given some open set, omega, my control set. If I go back to the original statement of theorem 1 in position. And now I'd like to draw the following sets. Gamma plus minus. They're going to be sets of trajectories. Let's call them, I don't know, rho in S star m, such that phi t of rho is not in the set omega, well, doesn't project to omega, for every t positive or negative. Okay. Now, the localization of your eigenfunction is invariant under the geodesic flow. And if you have an eigenfunction that is small in your omega, so it has small mass in omega, you can show it will have to be supported in those sets. Okay, there's quite a bit of heavy lifting that goes into these words, but let's just draw the sets. So you see, I have my omega here, omega, and I just look at, let's say, gamma plus, all the geodesics that when you go forward, they never intersect that set. That's a classical object. There's nothing quantum about it. And now what you see is that gamma plus is going to be foliated approximately, because omega has a boundary, by the flow in the stable directions. Right? If I have a point somewhere in S star m, I know that this geodesic never intersects omega in the forward direction. Well, if I perturb my point a little bit in the stable direction, the two geodesics will converge, so the other one will also not intersect omega. So your sets, and same for the flow direction. So you should think of the set gamma plus as being a union of 2-dimensional disks. So the leaves of this integrable foliation, E0 plus ES. What happens in the unstable case is different in the unstable direction. See, if I took an unstable curve, so then when I go, so if I perturb it in the unstable direction, the two geodesics will diverge exponentially fast. There's something called, let's say, unique ergodicity of the horocyclic flows, which tells you that at some point, this curve, when you expand it, will have to intersect omega. That's the only place where you use the omega is in an empty set. And from here, you can show that the set gamma plus is going to be porous in the unstable direction. And so you would see that your counterexample eigenfunction would have to localize in this dynamically defined set, which is nice in the flow and stable direction, and porous, so fractal in the unstable direction. And then when I switch plus to minus, the roles of stable and unstable directions are reversed. And then massaging it enough, you can arrive to a function that's localized on a fractal set in both stable and unstable direction, and that's where you hit it with fractal uncertainty principle. So the fractal set comes from dynamics, which is most fractal sets come from dynamics in one way or another, or some self-similarity, of just specifying a surface and this open set omega and looking at the trajectories that don't intersect it. Okay, sorry for running over, and thank you for your patience.
So principally, we have also used the time for questions, but maybe we have time for
in the middle.
one question. Yeah.
Thanks. So you were speaking about closed surfaces. Is
Yes.
it? But you cut a lot of things off. So how different is the problem, say, on hyperbolic plane? This may be a dumb question. I haven't.
Well, on the hyperbolic, so if your surface has a lot of infinite ends and your Laplacian doesn't have discrete spectrum, there are still questions, but they're formulated differently. In fact, this business started on convex co-compact surfaces, but sort of you have to formulate the question differently in terms of what's known as a spectral gap. I guess for the hyperbolic plane itself, the question would have a kind of direct answer because you have explicit formulas. But for surfaces with large infinite ends, so funnels, you have interesting questions that can be addressed. And those sets, instead of not hitting the holes, you would look at the sets of geodesics, which never escape to infinity.
Thanks.
So the last speaker of this first day of the conference is Ettore Minguzzi from University of Pisa, who will talk about the constancy of surface gravity or temperature for compact null hypersurfaces.
Yeah. Well, first of all, thank you to the organizer for thinking of me about this last opportunity to give this talk, last minute opportunity. As the title says, this is a mathematical problem, but it's related to some physical important questions because surface gravity is related to temperature. So this is going to be a talk about work with Sébastien Gurriaran and Raymond Onnompé. But I mean, the topic will be mostly differential geometric, but there are also some connection with geometric analysis. Let me recall that in Einstein general relativity, the spacetime is a differentiable manifold endowed with the metric of Lorentzian signature, and dynamics is expressed by the Einstein equations, where R is the Ricci tensor and T is the stress energy tensor. The results that you are going to obtain do not depend on this equation, but depend on the energy condition, only on the energy conditions that are derived from this equation. That is the null energy condition and the dominant energy condition. The spacetime is a connected time-oriented Lorentzian manifold. Point on spacetime are called events. We have a distribution of causal cone and the distribution of hyperboloids inside the cones. A curve is time-like depending on the sign of its square with this Lorentzian metric, like if it is 0. In my convention, this is negative for the time-like curve. It's causal if it is time-like or like. Now, 2 points connected by a causal curve are said to be causally related. If they are connected by a time-like curve, they are said to be chronologically related. A set is acausal if it has no two causally related distinct points, and achronal if it has no two chronologically related points. The null energy condition that we mentioned before is just the statement that Ricci contracted with any electric vector is larger than or equal to 0. And from the Einstein equation, we get that this is really related to the stress energy tensor. So this is a condition of energy positivity. Now, this condition controls focusing of surface orthogonal electric geodesics generated by a vector field n via the Ricciardo equation, where theta is the expansion and sigma is the shear of the congruence. The dominant energy condition, which is the other condition that will interest us, can be phrased in the following way. For every time-like vector, the map, this is T is the stress energy tensor, minus the stress energy tensor with one index raised, which in indices is like this, sends the time-like future cone into itself. It preserves the time-like falls inside itself after the map. Roughly, it states that energy does not flow faster than light. Okay, so it's bound on the speed of energy. So let S be a space-like hypersurface. A domain of dependence or Cauchy developments is the set consisting of all those P such that every inextendable causal curve passing through P intersects S. From the PDE's perspective, it's the portion of space-time predictable from data. Now, the future Cauchy horizon is essentially the future boundary. I mean, this is a technical definition. What is important is that if you take the boundary of the Cauchy development, future Cauchy development, it is the surface of the data itself plus the horizon, the Cauchy horizon. Now, a theorem tells us that this set is achronal. Through every point of this set, the future Cauchy horizon, passes a past inextendable like half geodesic contained in it. And these geodesics are called generators. So this is a picture to understand in a simple case of 1 plus 1 Minkowski, in which I remove 2 points. This is to understand the definition. So I remove 2 points from Minkowski. This is the surface S. And this is the Cauchy development, because if I pick any point, any continuous causal curve, past inextendable continuous causal curve, inextendable continuous causal curve intersect S. So it's in the future because this is past inextendable. However, this point here has a past inextendable causal curve that doesn't reach S because it goes to the removed point. So this point does not belong to the Cauchy development. This blue region here is the horizon, Cauchy horizon. Now, it can be noted that this horizon is non-compact. For instance, we have this region here. And is also non-smooth. For instance, we have a corner here. But there are other examples. For instance, this is Misner spacetime, a toy model, the 1 plus 1 dimensional spacetime with this metric. And here we have a region. Here, this is the cones. And these cones are tilted horizontally, essentially. So there exists closed time-like curves here. Then on this region, instead, the cones are oriented upward. And this closed line is in fact space-like because its tangent doesn't pass through the cone, but let's say outside the cone. Instead, this light-like geodesic in the middle is light-like, and it closes. So if I take this closed hypersurface, which is space-like, its past Cauchy horizon is precisely this curve. That is, this closed geodesic is the horizon, a past Cauchy horizon for this hypersurface, which in this example is one-dimensional. Okay. So on this region, we have even a global time. We have a time function that increases over every causal curve. In this region, instead, we have violation of chronology. So now this horizon is compact, is smooth. The generators running on it are incomplete. This is just a result of a simple calculation. And we say then that the horizon is non-degenerate because the it is incomplete, the geodesic, okay? Furthermore, it is scaling because this vector here is a like killing vector tangent to it. Then we say that the horizon is scaling. Now this theta is this theta here, and it's like for t equals 0. So t, yeah, this one, yes, it's always null, yes, but it's yes, the picture maybe is not the best. I mean, actually, yes, probably it's vertical, should have been drawn. The cones are not precisely these ones. Yes, I will. So all the talk is about that, essentially. Okay. So Cauchy horizons can be highly regular. In fact, Crucian and Galloway give an example of an horizon that is non-differentiable on a dense set. And this also extends to compact Cauchy horizon. So for a while, there was this problem, this conjecture of proving if under the null energy condition, a compact Cauchy horizon is actually smooth. And this was solved about 10 years ago by Larson and myself. So the theorem states this: suppose that the null energy condition holds, let H be SC0 compact future horizon, whose passing extendable generator are pass complete. Then H is smooth if the metric is smooth, analytic if the metric is analytic. Moreover, H is totally geodesic, and it's generated by an extendable like geodesic. Now, as you can see here, there is no Cauchy. It's just C0 compact future horizon, which I did not define actually. Essentially, it's the same thing as a Cauchy horizon without being Cauchy. That is, this property of Cauchy horizon is that if you pick a point, you have a generator running in the past direction. If I pick any point here, we have a generator running in the past direction that is contained in the horizon. This is what this property is what is used to define a C0 future horizon. It should be a topological hypersurface which is locally achronal, no time-like curve connecting any 2 points, such that if you pick any point of it, you can find a past inextendable like geodesic contained in the horizon. Then what happens in the case of a Cauchy horizon? There was a theorem by Hawking that for a Cauchy horizon, which is C2, the past generators are complete. So you would have this assumption for free. This theorem had to be generalized to the case of non-regular C0 to the C0 case. Okay, so required different methods. So in the end, for a C0 compact future Cauchy horizon, the generator are past complete, and so compact future Cauchy horizon under the null energy condition are smooth and totally geodesic. In fact, a horizon, there are several sorry, this result here is the result where the most geometric analysis enter, but I'm not going to cover this proof. I just mentioned that some techniques about semi-convexity of functions enter in this type of problem. In fact, I imported several results by Carlo Sinestrari to this setting. What is the idea? Suppose that this is the horizon, H. For every point, I know that there is a past inextendable like geodesic in it. So the trick, now what was known, what is simple to show, is that if you consider a point and you consider the cone, since it is locally achronal, if you pick a smaller cone, for sure, any time-like curve is not going to intersect twice the hypersurface. Okay, this means that this hypersurface is tilted more than this cone here, which means that the hypersurface is actually Lipschitz. Okay, but in fact, is what is called a lower C2 function. So it has a local graph which is semi-convex. Why so? Because if you pick a point P, you can find a point Q in the generator. You can take it arbitrarily close to P. And then you consider the light-like cone at Q. Let's say here there is a light-like cone, because remember that this one is light-like. And now you take the exponential map of the light-like cone. And this generates an hypersurface which essentially connects with the point Q, and which is smooth because it's the exponential map inside the convex neighborhood. Essentially, you start taking a convex neighborhood P and you pick Q inside the convex neighborhood. Then you use the exponential map to create a surface which is tangent to the horizon. This means that the horizon is supported by a C2 function from below, and so it is what is called a lower C2 graph. A lower C2 graph is essentially reduced by a C2 function plus a convex function. And from here, you can derive many results of regularity for horizons from Cauchy horizon. This is one of the first steps, and so on. Now, there is this horizon. This was particularly one of those results that can be accomplished using that strategy. The horizon is C1, equivalently differentiable at every point, if every light-like generator does not escape the horizon. Because the assumption is that the generators in the backward direction does not escape the horizon. This is what defines the horizon. But the problem is that it can escape in the future, okay? But in fact, it is differentiable if and only if these generators do not escape in both directions. Now, regularity then is not just a convenience assumed by mathematicians to ease their work when dealing with horizons. Regularity has physical meaning. So regularity issues are important as they are related to physical properties. If the regularity holds, light running in the direction of the horizon does not escape, which means it's trapped in the horizon. This is a physical property, cannot reach us. If the null energy condition holds, which is a physical property, then the compact Cauchy horizon is regular. Okay, so in reality, regularity it's a physical property here. In fact, the study of the relativity dynamics shows that regularity of the horizon is related to entropy. However, I'm not going to enter into this. Now, we are interested in the hypersurfaces now that result from the application of the previous theorems. And so we are going not to use the Cauchy property, but we are going to use those other properties, that H is a compact, connected, smooth, totally geodesic null hypersurface, and it's generated by the light-like geodesic. The light-like geodesic stay there in both directions. A Cauchy or compact Cauchy horizon under the null energy conditions has these properties. N shall always denote a smooth future-directed light-like vector field tangent to the manifold. Now, the second fundamental form is defined as an endomorphism. You need to essentially take the tangent space to the horizon and quotient with respect to the direction of these generators, which is n. And then this map B is just going to be nabla in the direction of x of this vector field n. Then you have to project, the bar means project to this space. This is well defined for instance, if you sum to x something proportional to n, it's cancel out this additional contribution. Now, over the generators, we have the Riccati-Ricciarduri equation, which is this one. And this old proposition by Capelli tells you that B equals 0 if and only if the covariant derivative of two vectors tangent to the horizon is tangent to the horizon. Essentially, the horizon is totally geodesic. So the totally geodesic condition is this B equals 0. So if I put B equals 0, then what do I get? That this nabla xn should be proportional to n. So this will be important. So the total geodesic property implies that the expansion and shear vanish, because this is the trace of B, this is the traceless part of B. And the Ricciardone equation implies that Ricci, evaluated on the tangent like vector, vanishes over the horizon. Now, as I was saying, B equals 0 is equal to total geodesic, but also it also implies that there is this one form omega, because now this nabla x n, if I don't take the quotient, must be proportional to n. So since it's linear in x, there should be a one form omega here. So this one form will be important. Now, if I choose x equal n, I get here the nabla n, and here omega n. I call omega n kappa, and can write this equation, which is a sort of a pre-geodesic equation. Now, we started with the field n, which can be arbitrary, because over the like hypersurface, I can rescale this vector field, and it's still like. We can scale it with a function. Then if I choose n prime in this way, then it's easy to see that omega changes by an exact form, and kappa prime becomes this expression here. Now, our main result established that under the dominant energy condition, n can be chosen so that this is actually a constant. This is the problem of establishing constant surface gravity. We will do that in the non-degenerate case, we shall see. Now, signature warning, like vectors do not admit a natural normalization. And due to the fact that generators accumulate on themselves on the horizon, because the horizon is compact, we have a quite intricate dynamics, potential very intricate dynamics of these generators. And in general, we cannot choose n such that it is geodesic. That is, geodesic is a special case, kappa k equals 0. But this is not acceptable in general, because if I start with a like geodesic, this is the vector. After running over the horizon, I might get close to the starting point. Even I can even be so lucky, let's say, that I get to the same point that the generator is closed. But the problem is that the vector is not the same as before. So I cannot choose a geodesic one because it would not globalize. The point is that you can choose pre-geodesic, not geodesic, with a constant. That's the idea. So the starting of all this thinking came from a simple example by Hawking, which is a closed geodesic, which is the example in Min's space-time as before. So suppose you take a segment gamma, which is closed. After an affine parameter lambda, I return to the same point with the tangent, which is proportional to the initial tangent, for some factor a larger than 1. Now, if you think about it, at the first, we can see the future inextendable lateral geodesic as a union of closed segment. In the first segment, the affine length is lambda. But in the second segment, since I start with a longer vector, longer by factor a, I get an affine contribution of affine length, which is lambda over a. And at the next step, I get lambda over a square. Each time I get forward, my contribution is smaller because the initial tangent vector to the segment becomes bigger. So in the end, you get a geometric series, and this converges. Okay. So a similar argument in the backward direction shows that the inextendable lateral geodesic covering gamma is future incomplete but past complete, essentially because in the past direction you get the inverse of the factor. However, in this future incomplete case, this like vector field, which is obtained rescaling gamma over the segment, gamma does not globalize because when you return it gets scaled. But this one corrects that problem in a linear way, and then this one is global. But then this one is pregeodesic. You calculate easily that there is a pregeodesic with this with constant, which is called surface gravity, which is constant, doesn't depend on t, and it's negative. So in summary, in this very simple example, you find if the factor of dilation of a tangent vector is larger than 1, you get negative surface gravity. The geodetic is future incomplete and past complete. If the factor is between 0 and 1, you get that the surface gravity is larger than 0. Geodetic is future complete and past incomplete. Only if the factor is equal to 1, then the geodesic tangent matches itself, and it turns out to be complete, obviously, in this case. Now, the problem is this very simple picture in one dimension holding in general? Higher dimension, the generators do not close. And for non-closed generators, here we need to drop A, because A is the dilating factor when I return to the same point. If I don't return to the same point, there is no such dilating factor. So the interest is this, the correspondence between this, is kappa constant exist? And if so, do we have still this correspondence between incompleteness and sign of kappa? And it seems to see that if kappa is constant, then yes, the answer is yes. The problem is to prove that there is one such choice with this constant value. If you have this constant value, then it's easy to see that all generators have the same completeness and incompleteness property. That is, there are all future incomplete or all past incomplete. What does one generator in terms of completeness? All the other generators do, which is very nice. In fact, what one does is actually in the proof is the first to show that they share the same completeness property, and then show that this k constant can be found. Now, a spacetime is globally hyperbolic if the follow. Let's start to other motivation for this type of problem. Spacetime is globally hyperbolic if the following equivalent properties hold. There is a space-like hypersurface said to be Cauchy, such that the whole spacetime is the Cauchy development of the hypersurface. That is, both the past and future Cauchy horizon are empty sets. Okay, there are other characterizations that do not interest us. Now, analysts would love if the spacetime were globally hyperbolic, as in this case, it would be determined by data on a Cauchy surface via Einstein equations. But the solutions of the exact solution of the Einstein equations tell us a different story. They are full of causal pathologies, even chronology violations, and so are often far from being globally hyperbolic. So the problem is not that of showing that non-global hyperbolic solution cannot exist, which is false, but that generic solution are globally hyperbolic, or that a space-time that cannot get nasty if it starts well-behaved. This motivates Penrose-Torr censorship conjecture that essentially states that under reasonable physical assumption, like genericity condition, energy condition, inextendable spacetimes have to be globally hyperbolic. Although usually formulated in a PDE context with use of Einstein vacuum equation, and that's Ricci flatness, this is really a statement about generic, physically reasonable, and thence non-empty spacetime. It's not a statement about empty spacetime. It's a statement about reasonable spacetime that might include matter. If the conjecture is true, then compact Cauchy horizons are also excluded. So we have here a rigidity case. Suppose that the spacetime is vacuum, so the energy condition all true. And as compact Cauchy horizon, that need must be non-generic, that is special. Okay, this is what cosmic censorship says. If you have a horizon, you must be special. What does it mean to be special? This leads to the Heisenberg-Moncrief conjecture. every smooth, compact null hypersurface, so generated by the geodesic, in a retrovacuum spacetime is actually killing. Namely, there exists a killing vector field tangent to the hypersurface. That is, to be special means if you have a compact Cauchy horizon, that's because the horizon is killing. You have a killing on the spacetime, and the killing is tangent to the horizon. That is, the horizon is special, it's a killing horizon, and the spacetime is special because it has a symmetry. Now, symmetry can exist if you have just an electron crossing the horizon, because it will be immediately break the symmetry. Okay, that is, symmetric spacetime do not exist in reality in the physical world. So this is sufficiently non-generic result in the spirit of Penrose. So they were able to prove the result under additional assumptions. The metric and horizon are analytic. The horizon generators are closed. Now, let n be the future directed attack vector field tangent to the horizon. We have already seen. We are going to define the surface gravity as this function. The problem is if it is constant. Now, it is well known that under the dominant energy condition, killing horizon have constant surface gravity, provided n is chosen equal to the killing vector. That is, to have constant surface gravity is a necessary condition to be killing. So you first prove that constant surface gravity is constant, then you prove that the horizon is killing. That's the idea. Now, in that setting, they prove also that, of course, if it is killing, surface gravity can be normalized to a constant, and they distinguish two cases: the degenerate horizon, zero surface gravity, and non-degenerate horizon, so non-zero surface gravity. And prove this picture. In the non-degenerate case, the generators are complete in one direction and complete in the other. The horizon is a Cauchy horizon. The killing field is space-like in the global hyperbolic region and time-like outside it. This is the picture of Misner spacetime. I've showed before. Essentially, qualitatively, is going to happen this thing. In the degenerate case, the generators are complete in both directions, and the horizon need not be Cauchy. So the main problem is extend previous results to the smooth case, drop the condition on the closure of the generators, and so prove the Heisenberg-Moncrief conjecture, which is essentially the cosmic censorship conjecture in the compact case, that is compact in the sense of horizons. Now, this point asks extend previous results to the no-smooth case. In particular, they assume that the horizon is smooth, but we have seen that we don't need to assume that because we have already shown, this was proved after the conjecture, that the horizon is as smooth as the metric if under the null energy condition. So the problem is to create the killing vector not while using the analytic assumption in the smooth category. So the first step is to prove that surface gravity is constant. This can be shown to imply that the Lie derivative of the spacetime metric is zero on the horizon. And then what you do is you push this condition outside the horizon. And then by pushing it outside the horizon, you construct the vector field n also outside the horizon, so creating the killing field. If you start essentially proving that n, you search for an n, a choice of n, at a scaling, such that the killing condition holds on the horizon. And then you need to extend the killing condition, showing that it holds in a neighborhood. And that will give you that the extension or a full killing field. So this is a problem. This extension problem is a problem of PD theory. This problem involves a lot of geometrical more geometric, more differential geometric. Now, there has been considerable progress in the non-degenerate case in recent years. And now, essentially, the first step was proved by this group, Bustamante Reis and Gurran and myself. And Peterson and Rax proved the extension, the hyperbolic PD problem extending N to a Killing field. So now the Eisenmenger-Moncrief conjecture is true in the non-degenerate case. More precisely, under the dominant energy condition, every totally geodesic, compact, smooth, null hypersurface admits an incomplete generator if and only if the surface gravity can be normalized to a non-zero constant. And so all generators are incomplete. And in this case, it is a Killing horizon and the Cauchy horizon bounded on one side by a region of chronology violation, which is precisely the picture of the Misner spacetime of the toy model. But of course, we are in higher dimension, the generator on the horizon do not close, and so on. Now, actually, so what is left is the degenerate case for which there were essentially no results up to recent times. So for a full proof of the conjecture, one possibility is to show that actually the degenerate Cauchy horizon do not exist. In fact, we do not know any example of the degenerate Cauchy horizon. But first, we need to understand general horizons, assuming they exist. To study something, you need to assume that it exists. Also, I don't think, anyway, I'm going to work, as I was saying, not with the Einstein equations. The Eisenmenger-Moncrief are assuming strongest Einstein equation. I'm not going to assume those. The extension requires the Einstein equation. The constant surface gravity does not. So recently, we realized that by using techniques of Riemannian flow theory, we could find a classification of all the possible horizons independently of degenerate or non-degenerate assumptions. And the theorem is this one. Under the dominant energy condition and this spacetime dimension 4, I mean, in less dimension is just a torus, the horizon. Okay? But in spacetime dimension 4, an oriented compact horizon has the possible mutually excluding structures. All generators are closed, and the manifold is a cipher manifold, where the flow is that of the closed loops of the cipher manifold. Only two generators are closed, and every other generator densely fill a two torus, and the horizon is a length space. In this case, only two closed generators. The other wind up forming a torus, essentially. Or every generator densely fills a two torus, and the horizon is a T2 bundle over S1, diffeomorphic to T3. Or every generator densely fills the horizon, and then the horizon is T3, and the flow is conjugate to a linear flow on the torus. Or finally, this is the most complicated, H is diffeomorphic to an hyperbolic fibration, and the flow is in the direction of one of the eigenvectors of this matrix that is used to construct it. Now, I don't know if I added something on. Oh, no, okay, then let me say something else which is not here. So this theorem, but for the last example, was obtained by Bustamante-Reiris in the non-degenerate case using theory from Lie groups, because in the non-degenerate case, you can show that there is a Riemannian metric left invariant on the horizon, and you can then use Lie group theory to obtain this type of result. Instead, to get the general case without non-degenerate assumptions, you need to use a Riemannian flow theory, and this gives then that for the degenerate horizon, all these structures are still valid, are still possible, but there is an additional one, which is this one, which is an example of so-called non-isometric Riemannian flow. A Riemannian flow is a flow such that locally there is on the quotient space a metric preserved under the flow. But it's on the quotient with respect to the direction of the flow. It's not a metric on the whole manifold. And then you can, so in the non-degenerate case, the flow is isometric, and you get only these 4 here. Now, what is the relation with stationary black holes? This idea of compact horizon is useful to study stationary black holes, because in a stationary black hole, there is a trick to hold that you can use the flow of this vector, Killing vector, to take the quotient with respect to the so-called one flow map. That is, you advance of time 1, and then you identify the points. But you have, if you choose this time of to construct this flow map, you can choose it wisely, and then there is one option that closes all the generators over the horizon. So actually, all the generators of the horizon close, and the event horizon of the black holes becomes a compact horizon with closed generators. And this can be used because, as I mentioned before, we have a regularity result for compact horizon that then you can lift, and you get that for stationary event horizons, they are as regular as the metric of the spacetime. There was a previous result by Cruciel and Lopez Costa that, however, used an assumption on sections of this horizon, which was essentially equivalent to a C1 assumption. Oops. But in reality, the compact horizon case is more general. Okay, you start from the stationary, you get something compact, but if you have result for compact horizon, they are much stronger. For instance, we can obtain, Hansi Petersen did use this strategy to obtain Hawking rigidity theorem, that there is another, in a stationary black hole, there is another Killing vector, axisymmetric Killing vector, by first projecting and finding the vector and then returning to the previous space. Now, physically, the physics is clear in black hole thermodynamics if you study Hawking temperature and you study black hole radiation. Then you get that the temperature of this radiation is related to the surface gravity by this formula. So establishing constant surface gravity means establishing the zeroth law of black hole thermodynamics, that the temperature in the stationary case is a constant. That's simply that. And the stationary condition, the temperature of a black hole is constant. Now, the remaining part of the talk is actually a sketch of the proof for the first step. That is how we prove that the surface gravity is constant in the non-degenerate case. Essentially, I can maybe go read some slides. I mean, I have some time. Maybe let's see if we find what are the key ideas. Then we start with the vector field n, and we denote with lambda of p the affine length of the geodesic that start with this vector n. So on every point you have a vector, and you consider the future light-like geodesic, and then you calculate the affine length. If you rescale the vector, we already saw that the one form omega changes like in this way. The affine length changes in this way, the surface gravity in this way, while these quantities here remain constant. Now, suppose that you know that lambda is multi-infinite. We don't know if that lambda is finite. We don't know that all generators are incomplete. Then if we choose this value for the rescaling, we easily find that lambda prime is constant. The affine length becomes constant. It's a choice such that if you take this factor, every geodesic that starts with that vector is has the same affine length 1. Now we have this lemma that if you take a generator, you parameterize it with the integral parameter of your vector field n, which is not geodesic. Starting from, so this is the geodesic x. Starting from x tau, then the future affine length starting from this point is given by this expression here. And now when you differentiate, you actually find that this affine length satisfies this differential equation. If lambda is found constant throughout the horizon, then you find that k is a constant on the horizon. Okay, so it is sufficient to prove that lambda is smooth and finite, and then you are done just by changing the vector field in this way. The problem is to prove that lambda is smooth and finite. And we do this in 2 steps. We start from an arbitrary choice, and under non-degeneracy, we prove that there is a smooth gauge transformation. Gauge is those rescalings, such that the surface gravity is negative everywhere. Not a constant, but at least negative. This uses a technique that we shall see in a moment that is called ribbon argument. Then the fact that k is less than 0 implies, which prove that implies that the new affine length for the new choice relative to the first gauge transformation is finite and smooth. This follows from the integral expression by showing that we can differentiate. And then with the second gauge transformation, which is the one I showed before, we get the result. Now I want to illustrate the idea up to what is called the ribbon argument, because it's the key idea, is one of the nicest idea of the proof. So we start from this lemma that tells you that if you pick 2 vector fields or tangent to the horizon, you have this identity just by calculations. This omega is the one form that we saw was related to totally geodesic assumption property. Now, assume the dominant energy condition and that the following property holds. If Ricci vanishes contracted twice with the electric vector, then Ricci is contracted with the electric vector is proportional to G contracted with the electric vector. Why is this true? This is it's quite simple, but it's key for all this argument. Well, first, we consider this expression here, which is actually the stress energy tensor. And we evaluate the stress energy tensor over x and over x. We simplify. If we have this value here, 0, we get 0, because x is like, so this also is 0. So now here we have a scalar product between a like vector and the image and the stress energy tensor of a causal vector, which must be causal by the dominant energy condition. But when you take the scalar product of 2 vectors that are future, 2 causal vector, then this can be 0 only if they are proportional. Okay, and so we get this proportionality. In particular, so Ricci contracted with x, since this is G contracted with x, is proportional to G of x. Sorry? The dominant energy condition is the condition that the stress energy tensor maps the future causal cone into the future causal cone, or the minus stress energy tensor. No, I mean, you can formulate it in many ways. If you formulate it as I expressed it in the beginning, which was via time-like vectors, then by continuity you get again that if this minus test energy tensor sends the causal cone into the causal cone. So the like this vector here, x is is sent by the stress energy tensor to a causal vector. So this one here in square bracket, it's a causal vector. A causal vector cannot have a scalar product with a causal vector, which is 0, unless they are the same vector up to a constant. If you pick two vectors on the future cone, the scalar product is not going to be 0 unless they are proportional. And that's okay. Yes, sorry. So we have, remember that we said that Ricci contracted twice with n is 0 because of the Ricciarduri equation. Was it one of the results of the theorem, essentially. Then we have that the assumption is satisfied for n. And so we have this relation here. But now, if you pick this equation here, you get that this quantity is proportional to g. So if y is tangent to the horizon, this is 0, because g of n of any vector on the horizon is 0. So you get that d omega n is 0. So this two form contracted with n is 0. And now I want to, well, this is the result I mentioned before, that the metric restricted to the horizon is actually invariant. Okay, but this is not. What I wanted to come to is the ribbon argument. It is, we introduce a one form, n star, and we split the tangent space to the horizon. So we have the vector n and this curve of this one form. This allows us to speak about horizontal curves, that are those that are in the kernel of n star. And via an argument on the certain projective bundle, we can show that this inequality is always true. And we come to this result that I describe in picture, more or less. I'm not going to read. This is what I do is I pick an horizontal curve and then two orbits, two generators on the horizon. So these are m-parameterized like geodesics. And then I close again the horizon with an horizontal curve. This is called a ribbon. Now we apply omega, we integrate omega over this boundary. And because applying Stokes' theorem, then you get d omega integrated over these two surfaces. But d omega, that two surface is spanned, one of the two vectors is n. Because all this surface is made by like generators. Okay. So we get that we are left just with the integral of the boundary. With this is the integral of omega over the horizontal curves. And this over the longitudinal curves. But the integral over the horizontal curves can be bounded. Why? Because omega is bounded by g. And g, restricted to the horizon, is invariant, as I expressed it before. It was, I mean, it is the totally geodesic, one of the way of expressing totally geodesic property, one of the many equivalent ways, is to say that the restriction of g to the hypersurface, the space-time metric, is invariant under the flow of n, provided you consider the metric restricted to the horizon. And then this integral is in fact has in fact a bound which is independent of the horizontal curve. It doesn't matter how you close the ribbon. That is, you can extend the ribbon and close it here, because this integral is actually bound, all these integral horizontal are actually bounded by the same number. And so you bound two of these two terms, and you get this result here. And now you push the generator to infinity to show that this integral of omega, the way it behaves, is independent of the generator. This is because if you pick two generators, it doesn't matter how elongated you pick them, the difference between the integral is going to be bounded. So if one goes to infinity, the other must go to infinity, and every other one must go to infinity. So, so we have this result. This integral converges to minus infinity, in particular, if the same happens to every other generators. And then the rest of it, I mean, there are many steps, but the next steps of the proof regard relating this behavior with the incompleteness of generator. We can show that if this integral goes to minus infinity, then the generator is incomplete. And so all generators are incomplete, provided there is one, and so on. So this is, at some point, for the second step, what we do, at some point, we need to show that certain, I mean, we make a gauge transformation which we show that kappa is negative, and then we define the new affine length. But this time we take advantage of the fact that this integral is bounded because the surface gravity is negative. So since it's compact, it's bounded from above by a negative constant. And then this affine length becomes bounded by an exponential. And when we take the derivative, we show that we get always polynomials times an exponential. And so that we can differentiate. And in the end, we show that there is an identity, which is this one here. The Hessian of this affine length is one term of a PD. And under reach equals 0, then there is another strategy that doesn't use reach equals 0. But let's assume reach equals 0, vacuum. Then we can bootstrap. Okay, so we have that the Hessian is something that depends on lambda, everything else is smooth, and so lambda is smooth. So we got that it is finite, that it is smooth. We make the last gauge transformation and find and prove and prove in this way. Okay. Okay, I stop here. Thank you.
Okay, thank you for this interesting talk. So are there questions?
So this major theorem you stated was in 4 dimensions. Is this because Lie groups behave differently in high dimensions? Or is there something inherently 4-dimensional about this ribbon argument?
You mean the theorem of classification theorem? No, the classification theorem has nothing to do with the ribbon argument and with the constancy of surface gravity in reality. It's a theorem on Riemannian flows, which require just the total geodesic property. Yes, essentially we discovered that a lot of results could be imported from this theory, and so that result comes from a result by Carrière, a French mathematician, that extended the previous result of Lie group theory to the Riemannian flow case.
Thank you. So for the Moncrief-Eisenberg theorem conjecture, so where do you use compactness of the null hypersurface? And also, do you assume compactness in the sense it has no boundary, like compact without boundary?
Okay, well, I think there are several steps in which we use compactness. For instance, when I stated there is an upper bound using a projective, okay, this, no, this one. Okay, for instance, here, we want to bound omega. We need a bound because omega is not left invariant by the flow, but the space-time metric is left invariant by the flow. So the idea is I want to push the ribbon as long as possible, but I want the bound, the integral of omega in the horizontal direction to stay bounded. Well, I bound it with something that is invariant, which is G. To bound it, we consider this ratio, and this is invariant under the scaling of X. This means that it lives in the projective bundle, which is the projective bundle of the kernel of this one form and star. And this projective bundle is then compact because it's over a compact. And then the constant exists. Otherwise, that constant does not exist. This is an example of,
Thank you.
of one place.
I have a question about the constant surface gravity equation. Are solutions locally expected to be unique or to depend on I mean, or should there be like moduli spaces?
You mean if it is you? Okay, the surface gravity, when we say constant surface gravity, actually you can rescale the vector n by any constant, positive constant, and this rescale the constant surface gravity, which then changes. So what is really constant is positive, the sign. Now, in black hole physics, you can associate with the temperature because you cannot rescale the vector field, because the vector field is the Killing field. You want the Killing field at infinity to be normalized to 1 to represent an observer, and then you cannot rescale it. And this implies that the surface gravity, it's interesting not just on its sign, but also on its value. Now, in the compact case, I think it depends on the dynamics of the generators. If you can, how many solutions you can find. If you have closed generators, you can, I think, find many type of rescaling that gives you a constant surface gravity. For instance, if you have the geodesic case and you have all closed, if you have a T2 bundle over, or if you have many closed geodesics, you multiply by a function that is constant over this geodesic. You rescale in a constant way over each geodesic. You still get a geodesic field, but the surface gravity, no, in this case changes. No, I think, no, sorry, I think we have one theorem about uniqueness somewhere. Sorry, no, yes, in the last paper there is a theorem about uniqueness. I should maybe we can check it together. Yes, maybe there is some uniqueness in this vector, in the vector field n, let's say. Surface gravity as a constant, you can push it normalize it at a value you want.
I was wondering
about the vector field.
Yeah. That's
no, the vector field is. I think it's unique, but I need to check. We can check it together. Don't remember the statement now.
Okay, thanks.
Okay, if there are no more questions, then we are finished the session of today. We thank again our speaker and all the speakers of this first session.